Hello there and welcome back to the Science Sleepy Minds, that cozy corner of the internet where we turn the incomprehensible vastness of existence into something resembling a bedtime story. Tonight, you find yourself standing at the edge of revelation, teetering on the precipice of cosmic understanding that would have made astronomers from just a decade ago weep into their coffee mugs. Picture this. Right now, as you settle into your pillows and adjust your blankets, a golden hexagonal mirror roughly the size of a tennis court floats silently through space, 1,000,000 miles from Earth, staring deep into the heart of the galaxy you call home. And what it has found there is nothing short of extraordinary. The Milky Way, that familiar band of light our ancestors traced across summer skies, that celestial river they wove into myths and legends, turns out to be something far grander, far older, and far more mysterious than we ever dared to imagine. You probably will not survive the true comprehension of what we're about to explore together, not because it is dangerous, but because the human mind genuinely struggles to process scales this enormous without short-circuiting somewhere around the third or fourth zero. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. I would love to know where you're listening from tonight, so drop your location and local time in the comments below. Let us see how far across this spinning planet our little community stretches. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The James Webb Space Telescope changed everything in December of 2021, though we would not fully grasp how profoundly until the data started flooding back to Earth in the months and years that followed. You see, for generations, astronomers have been doing their best to measure our galactic home using tools that, while revolutionary for their time, were fundamentally limited in ways we did not entirely appreciate. It is a bit like trying to survey a vast forest while standing in the middle of it during a foggy morning, knowing there are trees all around you but only able to see clearly for a few hundred feet in any direction. That fog, in cosmic terms, is dust. Interstellar dust, to be specific, those countless tiny particles of carbon and silicates and ice that drift between the stars, absorbing and scattering visible light with frustrating efficiency. For over a century, this dust acted as a cosmic curtain, hiding significant portions of the Milky Way from our most sophisticated optical telescopes. Then Webb arrived with its infrared eyes, and suddenly the curtain was drawn back. The historical context here matters more than you might initially think. Back in 1785, William Herschel attempted the first systematic mapping of the Milky Way by counting stars in different directions, essentially trying to determine the shape of our galaxy by noting where the stellar population seemed thickest. His conclusion was that we lived in a flattened disk of stars with the sun positioned somewhat near the centre. He was partially right about the disk part, at least. By the early 20th century, astronomers like Harlow Shapley had realised our position was far less central than Herschel imagined, shifting our cosmic address to the galactic suburbs rather than downtown. But even then, the size estimates were rough, the boundaries uncertain, the true extent of our stellar city lost in that impenetrable haze of interstellar dust. The numbers you grew up learning, assuming you paid any attention during those astronomy units in school, probably placed the Milky Way somewhere around 100,000 light-years in diameter. That figure appeared in textbooks, documentaries, planetarium shows, and countless Wikipedia articles for decades. It was a nice, round number, satisfyingly comprehensible despite representing a distance so vast that light itself, the fastest thing in the universe, would need 100 millennia to traverse it. But here is the thing about nice round numbers in science. They tend to be placeholders, best guesses that stick around until better measurements come along. Webb brought those better measurements, and the Milky Way suddenly got a lot bigger. The initial data releases began painting a picture of a galaxy that extended well beyond those comfortable 100,000 light-year boundaries. Stellar populations appeared in regions previously thought to be empty intergalactic space. Structures emerged from the infrared murk that had no business being where they were according to older models. Scientists still argue about the exact figures, as they always do when paradigms shift, but the emerging consensus suggests our galaxy might stretch closer to 200,000 light-years across, possibly more when you factor in the faint outer halo of ancient stars that surrounds the visible disk, like a ghostly sphere. Double the size means more than just bigger numbers on a chart. It means more stars, potentially hundreds of billions more than previous estimates suggested. It means more mass, which has profound implications for everything from dark matter calculations to predictions about our eventual collision with the Andromeda Galaxy. It means more history, more cosmic archaeology hidden in those distant stellar populations that Webb is only now bringing into focus. There is something almost humbling about discovering that your home is larger than you thought, that the walls extend further into the darkness than your candle ever illuminated. Humans have experienced this sensation before, of course. We thought Earth was the centre of everything until Copernicus politely suggested otherwise. We thought the Sun was a fairly typical star until we realised it sits in the top 10% by mass. We thought our galaxy was the only one until Edwin Hubble looked through his telescope at Mount Wilson and spotted countless other island universes scattered across the void. Each revelation expanded our cosmic perspective while simultaneously shrinking our sense of importance. The Webb discoveries continue this grand tradition of finding out we are smaller than we imagined while the universe around us grows ever more magnificent. The quirky detail that historians of science will probably argue about for decades is this. We had hints that something was off with our Milky Way measurements for years before Webb launched. Radio telescopes and infrared surveys from ground-based observatories had detected anomalies, stellar populations in unexpected places, gravitational signatures that did not quite match the models. But the data was patchy, the error bars wide, and the astronomical community is nothing if not conservative when it comes to rewriting textbooks. It took the crisp, clear infrared vision of Webb, unobstructed by Earth's atmosphere and equipped with instruments specifically designed to peer through cosmic dust, to provide the definitive evidence that could no longer be explained away or dismissed as instrumental artifacts. You're lying there, perhaps already feeling the edges of drowsiness creeping in, and the galaxy overhead stretches twice as far as you learned in school. Somewhere out there, in regions we could not even see until a few years ago, stars burn and planets orbit and cosmic processes unfold in complete indifference to whether any intelligence ever notices them. Webb has given us new eyes, and what those eyes reveal is a Milky Way grander and more ancient than our limited vision ever suggested. The old maps were wrong, and the fascinating part is how confidently wrong they managed to be for so remarkably long. You find yourself now drifting through the history of galactic cartography, that peculiar discipline where scientists attempt to draw accurate maps of a structure they are trapped inside of, like a bacterium trying to sketch the complete anatomy of the whale it inhabits. For over a century, astronomers squinted at the heavens through increasingly sophisticated instruments, crunched numbers with increasingly powerful computers, and arrived at measurements that seemed authoritative enough to print in textbooks and etch into the public consciousness. Yet those measurements, we now understand, were fundamentally compromised by factors that seem almost embarrassingly obvious in hindsight. The story of our galactic miscalculations begins, as so many astronomical stories do, with the limitations of light, specifically visible light, that narrow slice of the electromagnetic spectrum our eyes evolved to detect because it happens to penetrate Earth's atmosphere efficiently. When you build telescopes designed to gather visible light, you see the universe in the same wavelengths your naked eye perceives, just with far greater magnification and sensitivity. This seems perfectly reasonable until you realize that visible light represents only a tiny fraction of the information radiating through space, and worse, that it is particularly susceptible to absorption and scattering by dust particles. Imagine trying to measure the size of a grand ballroom while someone continuously pumps theatrical fog into the space. You might see the chandelier overhead, the nearby dancers, perhaps the outlines of the far wall if you squint, but your measurements would inevitably underestimate the room's true dimensions because the fog obscures everything beyond a certain distance. Now imagine that fog is not uniform but clumps in some areas and thins in others, creating misleading clear patches that suggest boundaries where none exist. This is essentially the situation astronomers faced when attempting to map the Milky Way using optical telescopes. The interstellar medium, that diffuse material scattered between the stars, contains enough dust to block or dim the light from distant stellar populations, making the galaxy appear smaller and less populated than it actually is. The historical figures who attempted these early measurements deserve credit for their ingenuity, even as we acknowledge their errors. In 1920, the famous Great Debate took place between astronomers Harlow Shapley and Heber Curtis at the Smithsonian Institution, arguing about whether the fuzzy spiral nebulae visible in telescopes were part of our own galaxy or separate island universes entirely. Shapley ironically argued that the Milky Way was enormous, perhaps 300,000 light-years across, and that those nebulae were relatively nearby gas clouds. Curtis believed our galaxy was smaller and the nebulae were distant external galaxies. History proved Curtis correct about the external nature of those nebulae, but the debate itself reveals how uncertain even basic galactic dimensions remained well into the 20th century. The numbers stabilized somewhat by mid-century, settling into that familiar 100,000 light-year diameter that appeared in countless educational materials. This estimate came from various techniques: counting stars in different directions, measuring the distribution of globular clusters, tracking the motions of gas clouds in the galactic disk. Each method had its own assumptions and limitations, its own sources of systematic error that were difficult to quantify. When multiple independent techniques converged on similar figures, astronomers gained confidence that they were approaching the truth. What they failed to adequately account for was that all these techniques shared a common vulnerability to the same obscuring dust. Here is the quirky historical detail that makes this story even more interesting. Astronomers actually knew about interstellar dust absorption by the 1930s, when Robert Trumpler demonstrated that distant star clusters appeared dimmer and redder than their distances would predict, evidence that something was absorbing and scattering their light along the way. Yet incorporating dust corrections into galactic models proved surprisingly difficult because the dust distribution itself remained poorly mapped. You cannot correct for obscuration if you do not know where the obscuration is thickest. It was a classic catch-22 situation that persisted for decades. The numbers you encounter still in older books represent genuine scientific effort, but they also represent a particular era's technological capabilities and conceptual frameworks. When astronomers in the 1980s and 1990s quoted the Milky Way's diameter as 100,000 light-years, they were not lying or being lazy. They were reporting the best estimates available given the tools at hand. The error bars on those estimates were larger than often acknowledged, but the culture of scientific communication tends to favour clean, confident numbers over honest expressions of uncertainty. Nobody wants to read a textbook that says the galaxy is probably somewhere between 80,000 and 200,000 light-years across, depending on how you define the boundaries and which systematic errors you think matter most. The paradigm began shifting in the 2000s as infrared surveys from ground-based observatories and earlier space telescopes started revealing structures beyond the presumed galactic edge. The Sloan Digital Sky Survey detected stellar streams and dwarf galaxies at unexpected distances. The 2-micron All-Sky Survey, or 2MASS, mapped infrared sources across the entire celestial sphere, finding stars in regions that optical surveys had written off as empty. Each discovery chipped away at the comfortable 100,000 light-year consensus, but the data remained fragmentary enough that the textbook numbers persisted through inertia. Then came Gaia, the European Space Agency's remarkable mission to measure the positions and motions of over 1 billion stars with unprecedented precision. Gaia's data releases in 2016 and 2018 provided 3-dimensional maps of stellar populations throughout the Milky Way, revealing structures and movements that previous surveys had missed. Scientists still argue about how to interpret Gaia's findings, but the general trend pointed toward a larger, more complex galaxy than traditional models described. The stage was set for Webb to provide the definitive infrared observations that would rewrite our understanding completely. What strikes you as you lie there contemplating this history of error and correction is how the scientific process actually worked as intended, even when the interim conclusions were wrong. Measurements improved as instruments improved. Models evolved as data accumulated. The 100,000 light-year estimate was never meant to be eternal truth, merely the best available approximation pending better observations. Webb delivered those better observations, and the Milky Way obligingly revealed itself to be grander than our limited vision had suggested. The galaxy did not change, of course. It has been exactly as large as it actually is for billions of years, utterly indifferent to human attempts to measure it. What changed was our ability to perceive what was always there, hidden behind curtains of dust, waiting patiently for instruments sensitive enough to penetrate the cosmic murk. You rest your head on your pillow, knowing that the stars overhead stretch twice as far as your childhood planetarium shows claimed, and somehow this makes the night feel both larger and more intimate simultaneously. Infrared vision changes everything, and the transformation it brings to astronomy parallels those moments in human sensory evolution when entirely new categories of experience suddenly become accessible. You are now floating through the electromagnetic spectrum, that vast continuum of radiation stretching from gamma rays shorter than atomic nuclei to radio waves longer than football fields. And somewhere in that spectrum lies a band of light your eyes cannot detect, but which carries secrets the visible universe keeps hidden. Infrared radiation, with wavelengths just beyond the red edge of human perception, penetrates cosmic dust the way visible light cannot, and this single fact has revolutionized our understanding of the galaxy we inhabit. The physics here is beautifully straightforward once you grasp it. Dust particles in space tend to be roughly the same size as the wavelengths of visible light, which means they interact strongly with photons in that range, absorbing and scattering them efficiently. Think of waves in a harbour encountering a breakwater. If the wavelength of the waves roughly matches the size of the obstacles, the waves get disrupted dramatically. But if the waves are much longer than the obstacles, they simply flow around them with minimal disturbance. Infrared wavelengths are longer than the dust particles they encounter, allowing them to pass through dusty regions that would completely block visible light. It is not that infrared radiation ignores dust entirely, but its interactions are weak enough that astronomers can see much deeper into obscured regions than optical telescopes ever could. The James Webb Space Telescope was designed from the beginning to exploit this infrared advantage to its absolute maximum potential. Its primary mirror, that iconic golden hexagon composed of 18 beryllium segments coated with a microscopically thin layer of gold, reflects infrared light with exceptional efficiency. Gold makes an excellent infrared reflector, which is why Webb appears golden rather than the silvery aluminum-coated mirrors of optical telescopes like Hubble. Behind that mirror sit 4 scientific instruments optimized for different infrared wavelength ranges, each capable of detecting heat radiation from objects barely warmer than absolute zero, and the entire observatory floats at the second Lagrange point, a gravitationally stable location where Earth, Sun, and Webb's massive sunshield conspire to keep the telescope perpetually cold and dark, essential conditions for sensitive infrared observations. The historical irony that astronomers love to mention is that William Herschel, the same astronomer who attempted the first Milky Way map in 1785, accidentally discovered infrared radiation in 1800 while measuring the temperatures of different colours of sunlight with a thermometer. He noticed that the thermometer registered the highest temperature when placed just beyond the red end of the visible spectrum in a region where no light appeared visible. He called this invisible radiation calorific rays, and for 2 centuries afterward, astronomers dreamed of building telescopes that could see in this hidden wavelength range. Webb represents the culmination of that 200-year dream, an instrument Herschel could scarcely have imagined that fulfills the promise his thermometer first suggested. When Webb turned its infrared gaze toward the Milky Way's dustiest regions, the results exceeded even optimistic expectations. The galactic center, that crowded and chaotic region where stars orbit a supermassive black hole in a gravitational frenzy, had been studied extensively by previous infrared observatories like Spitzer and ground-based telescopes using adaptive optics. But Webb's combination of sensitivity, resolution, and wavelength coverage revealed details those earlier instruments could never achieve. Structures emerged from the murk that challenged existing models. Star-forming regions previously hidden behind dust clouds became visible in stunning clarity. Ancient stellar populations lurking at the galaxy's outskirts finally registered on scientific instruments for the first time. The quirky detail that catches many people off guard is that Webb does not actually see heat in the way popular descriptions sometimes suggest. Rather, it detects infrared photons emitted by objects across a wide temperature range, from the cold dust grains drifting between stars to the warm planets orbiting distant suns. Everything warmer than absolute zero radiates some amount of infrared light, and the specific wavelengths of that radiation depend on temperature. Webb's instruments can pass these wavelengths with extraordinary precision, allowing scientists to determine not just where objects are located, but what temperatures they possess, and, through spectroscopy, what chemical elements they contain. Scientists still argue about how to best calibrate and interpret Webb's infrared data, particularly when comparing observations to theoretical models developed using older instruments. The transition from one generation of telescopes to another always involves a period of adjustment as the community learns the new instrument's quirks and limitations. But the fundamental insight remains robust. The Milky Way contains vastly more structure than visible light observations suggested, and much of that structure was hidden behind dust that infrared radiation easily penetrates. You might wonder why astronomers did not simply point existing infrared telescopes at these dusty regions earlier and discover what Webb eventually found. The answer involves both technical limitations and the particular genius of Webb's design. Ground-based infrared telescopes must contend with Earth's atmosphere, which absorbs many infrared wavelengths and emits its own thermal radiation that creates noise in astronomical observations. Space-based infrared telescopes like Spitzer operated for decades and made remarkable discoveries, but their smaller mirrors and less sensitive detectors could not match Webb's capabilities. It is a bit like comparing a candle to a searchlight. Both produce light, but only one can illuminate distant objects hidden in darkness. The transformation in our galactic understanding happened remarkably quickly once Webb's data began flowing. Within months of the first observations, papers appeared describing stellar populations in the outer galaxy that previous surveys had missed entirely. Within a year, the first revised estimates of galactic dimensions began circulating through the astronomical community, tentative at first, but growing more confident as independent analyses converged on similar conclusions. The Milky Way had not grown larger, of course. It had simply become visible in ways it never was before, and what became visible demanded a fundamental revision of everything astronomers thought they knew about their home galaxy. You lie there in the comfortable darkness of your room, perhaps noticing how the concepts themselves seem to glow with an inner warmth, like infrared sources revealing themselves to sufficiently sensitive instruments. The universe has always contained more than human eyes evolved to perceive, and every new detector technology reveals fresh wonders hidden in wavelengths we cannot naturally see. Webb's infrared vision represents the latest chapter in this ongoing unveiling, and the Milky Way it reveals stretches far beyond the boundaries drawn by astronomers who could only see invisible light. Counting stars nobody knew existed sounds like the setup for an impossible task, yet this is precisely what Webb's observations have enabled, and the numbers that emerge from this cosmic census are staggering enough to make even seasoned astronomers pause and recalculate. You find yourself now immersed in the mathematics of stellar populations, that branch of astronomy where scientists attempt to estimate how many stars inhabit a galaxy by combining direct observations with statistical extrapolations, and where even small adjustments to baseline assumptions can shift final counts by billions. The traditional estimate for the Milky Way's stellar population hovered somewhere between 100 billion and 400 billion stars, a range so wide it reveals how uncertain astronomers actually were despite the confident single numbers that appeared in popular accounts. The lower bound came from direct counting of stars bright enough to register on surveys, extrapolated to include fainter objects below detection thresholds. The upper bound incorporated theoretical models of stellar formation and death rates, gas distribution, and dark matter content. Both approaches relied heavily on assumptions about regions of the galaxy that optical telescopes could not observe directly, particularly the dust-obscured central bulge and the faint outer halo. Webb has begun filling in precisely these gaps, and what it finds suggests the true number sits comfortably above 400 billion, possibly approaching 500 billion stars or more. The galactic core alone, that dense region within a few thousand light-years of the central supermassive black hole, contains stellar populations so crowded and complex that previous estimates seriously undercounted them. Infrared observations cut through the dust that made this region appear relatively sparse in optical surveys, revealing a riot of stars packed so densely that individual objects become difficult to distinguish even with Webb's exceptional resolution. The historical context for stellar population estimate stretches back to the early 20th century, when astronomers first began attempting systematic counts of stars in different regions of the sky. Jacobus Kapteyn, a Dutch astronomer working in the early 1900s, developed statistical methods for estimating total stellar numbers based on limited observations, essentially pioneering the techniques that would be refined over the following century. His estimates were wildly wrong by modern standards, but the methodology he established proved sound. Observe what you can, understand the selection effects that limit your observations, and extrapolate carefully to estimate what you cannot see. The quirky detail that makes this counting exercise particularly interesting involves the faint end of the stellar mass distribution. Stars come in an enormous range of sizes, from blue supergiants hundreds of times more massive than the Sun to red dwarfs barely massive enough to sustain nuclear fusion in their cores. The relationship between stellar mass and abundance follows a pattern astronomers call the initial mass function. For every massive bright star that forms, nature produces many more small dim ones. Red dwarfs outnumber sun-like stars by roughly 10 to 1, and they outnumber massive blue giants by factors of thousands. But red dwarfs are so faint that detecting them at galactic distances pushes telescopes to their absolute limits. Webb's infrared sensitivity allows detection of red dwarfs at distances where optical telescopes would see nothing at all. These small, cool stars emit most of their radiation in infrared wavelengths, making them perfect targets for Webb's instruments, even when interstellar dust dims their already feeble light further. The surveys emerging from Webb's first years of operation have identified red dwarf populations in the outer galaxy and galactic halo that simply did not appear in previous catalogues, adding billions of stars to the Milky Way's census that nobody knew existed a few years ago. Scientists still argue about how to properly extrapolate from Webb's limited survey regions to the galaxy as a whole. No telescope, not even one as powerful as Webb, can individually observe every star in the Milky Way. The galaxy is simply too vast, the stars too numerous, the telescope time too precious. Instead, astronomers observe representative samples of different galactic regions and apply statistical methods to estimate total populations. The arguments concern which regions count as truly representative, how to correct for selection effects that might bias the samples, and whether the initial mass function remains constant across different galactic environments, or varies in ways that affect extrapolations. The emerging consensus, though still subject to revision as more data accumulates, suggests the Milky Way hosts somewhere between 400 billion and 600 billion stars, with the most likely value around 500 billion. This represents a significant upward revision from the numbers that appeared in textbooks just a decade ago, and the revision comes primarily from two sources: previously undetected red dwarfs in the outer galaxy and galactic halo, and dense stellar populations in the dust-obscured galactic center that optical surveys dramatically undercounted. 500 billion stars. The number rolls off the tongue easily enough but resists genuine comprehension. If you counted one star per second, never sleeping, never pausing, dedicating your entire existence to the count, you would need roughly 16,000 years to reach 500 billion. The entire span of recorded human history would not suffice. Every star you've ever seen in the night sky, every point of light that ancient navigators used to cross oceans and that poets have invoked in verses for millennia, represents an infinitesimal fraction of the total stellar population surrounding you. And most of those stars remained completely invisible to every human who ever lived, until a golden mirror floating at the edge of Earth's gravitational influence turned its infrared gaze toward them. The implications extend beyond mere numbers. More stars mean more planets, since nearly every star observed closely enough appears to host at least one planetary companion. More stars mean more locations where interesting chemistry might occur, where the conditions for life might arise, where complexity might emerge from simplicity, as it did on at least one rocky world orbiting an unremarkable yellow dwarf in an unfashionable arm of this vast galactic metropolis. The census Webb enables is not merely an exercise in astronomical bookkeeping, but a preliminary survey of cosmic real estate we're only beginning to appreciate. You drift further into the warmth of your covers, surrounded by the conceptual weight of 500 billion stellar furnaces burning across distances your mind cannot truly grasp. Each one is a sun, many older than the one that warms your days, many hosting worlds we will never visit, all participating in the grand gravitational dance that holds the Milky Way together as it spirals majestically through the void. The detection methods Webb employs deserve brief elaboration as you settle into this numerical enormity. The telescope does not simply photograph regions of the sky and count dots of light. though that oversimplification captures the basic concept. Instead, sophisticated image processing algorithms analyze the data, distinguishing genuine stellar sources from instrumental artifacts, background galaxies, and cosmic rays that mimic point sources. Each detected object must meet statistical thresholds for reliability, and borderline detections require follow-up observations for confirmation. The process is painstaking, automated where possible, but requiring human judgment at critical junctures, and the stellar catalogues that emerge represent years of careful analysis. The galactic disk stretches further than anyone imagined, and this discovery carries you now toward the outer reaches of the Milky Way, into territories previous generations of astronomers had written off as empty intergalactic void. Picture the galaxy as a luminous frisbee spinning through space, its central bulge surrounded by graceful spiral arms that trail outward like the wake of a cosmic pinwheel. The edge of that frisbee, the boundary where organized galactic structure yields to the formless darkness between galaxies, turns out to be considerably more distant than the 100,000 light-year radius that textbooks long proclaimed. Webb's observations have identified stellar populations at distances exceeding 150,000 light-years from the galactic center, and some detections suggest organized structures extending even further. These are not isolated rogue stars ejected by gravitational encounters, though such objects certainly exist. Rather, Webb reveals coherent stellar streams and faint extensions of the spiral arms themselves, populated by stars that clearly belong to the Milky Way, despite residing in regions previously considered empty. The disk does not end where optical telescopes suggested it ended. It merely fades beyond the detection threshold of instruments limited to visible wavelengths. The historical understanding of galactic disks evolved considerably over the 20th century, driven by increasingly sophisticated observations and theoretical models. Early estimates of the Milky Way's disk radius relied heavily on measurements of the galactic rotation curve, the relationship between orbital velocity and distance from the galactic center. Radio telescopes could track the motion of hydrogen gas throughout the disk, and the rotation curve suggested the disk extended roughly 50,000 light-years from center to edge. This measurement became canonical, appearing in textbooks and review articles for decades, though it always came with caveats about uncertainty in the outer regions where observations became sparse. The complication, which astronomers appreciated but could not fully resolve, until Webb, involved the distinction between where the disk contains detectable material and where it actually ends. A disk can extend well beyond the region where traditional surveys detect stars or gas, hosting faint stellar populations that fall below detection thresholds. It is similar to a city whose lights gradually dim toward the suburbs and eventually fade into countryside darkness. The municipal boundary does not necessarily coincide with where the streetlights stop being visible from space. The Milky Way's disk, Webb now reveals, extends well into what previous observations treated as the dark countryside beyond the city limits. The stellar populations in these outer regions possess characteristics that fascinate astronomers attempting to reconstruct the galaxy's history. Many appear quite old, with chemical compositions suggesting they formed in earlier cosmic epochs when the universe contained fewer heavy elements. This makes sense given theoretical models of galactic assembly, which predict that galaxies grow from the inside out, with newer stellar generations adding material to the outer disk over billions of years. The ancient stars in the far disk represent some of the earliest generations to form in the Milky Way's environment, survivors from an era when the galaxy was still assembling itself from primordial gas clouds. Here is the quirky detail that makes the outer disk discoveries particularly intriguing. Some of the stellar streams Webb has identified appear to be remnants of dwarf galaxies that the Milky Way consumed through gravitational capture and tidal disruption. The galaxy, it turns out, has been cannibalizing its smaller neighbours for billions of years, stripping stars from captured dwarfs and incorporating them into extended structures that now populate the outer disk and halo. Scientists still argue about how many of the outer disk stars formed in situ versus how many arrived as immigrants from devoured companion galaxies. But both populations clearly contribute to the extended structure Webb reveals. The techniques for measuring stellar distances at these extreme ranges push the limits of current astronomical capabilities. Parallax measurements, the gold standard for stellar distances, become unreliable beyond a few thousand light-years because the angular shifts caused by Earth's orbital motion become too small to measure accurately. Instead, astronomers rely on standard candles, objects whose intrinsic brightness is known or can be inferred from other observable properties. Cepheid variable stars, whose pulsation periods correlate with their luminosities, serve this purpose for intermediate distances. For the faint outer disk populations Webb detects, astronomers use red giant stars whose properties follow predictable patterns that allow distance estimation from colour and brightness measurements. The revised disk dimensions have immediate implications for calculations of galactic mass and dark matter content. The rotation curve that astronomers use to infer the presence of dark matter depends on knowing how far the disk extends and how stars move at different radii. A larger disk means the rotation curve extends further than previously measured, providing additional constraints on dark matter distribution models. Early analyses of Webb data suggest the dark matter halo surrounding the Milky Way may be more massive than previous estimates indicated, though scientists continue debating the precise implications. You might wonder whether these distant disk populations matter for anything beyond academic interest, and the answer involves the future trajectory of the galaxy itself. The Milky Way is currently approaching the Andromeda Galaxy at roughly 250,000 miles per hour, destined to collide and merge in approximately 4 to 5 billion years. The dynamics of that merger depend heavily on the mass and extent of both galaxies. A larger, more massive Milky Way will interact differently with Andromeda than the smaller galaxy older models described. The collision will not destroy either galaxy, but rather merge them into a larger elliptical system astronomers have nicknamed Milkomeda, and the extended disk populations Webb discovers will participate in that cosmic restructuring alongside the more familiar inner regions. The outer disk also serves as a laboratory for studying galactic dynamics in regimes where theoretical predictions become uncertain. Stars at extreme radii orbit the galactic centre so slowly that their orbital periods exceed the age of certain stellar populations, meaning some outer disk stars have not yet completed a single orbit since they formed. These long orbital timescales preserve signatures of gravitational perturbations and past interactions that would be erased by dynamical mixing in the faster-moving inner regions. Webb's detection of these stellar populations opens windows into galactic history that were previously inaccessible. You relax into the sensation of the galaxy expanding around you, its boundaries receding toward distances that dwarf the already immense scales you learned as a child. The disk beneath your cosmic feet extends further than any map suggested, populated by ancient stars whose light has been travelling toward Webb's detectors for hundreds of thousands of years. The Milky Way you inhabit is not merely 100,000 light-years of organised stellar society, but something grander, something that stretches into the darkness between galaxies and contains multitudes astronomers are only beginning to census. Dark matter's hidden architecture surrounds you now, that invisible scaffolding upon which the visible galaxy hangs like luminous ornaments on an unseen tree. You've likely heard of dark matter before, that mysterious substance comprising roughly 27% of the universe's total mass energy content, detectable only through its gravitational influence on visible matter, never directly observed despite decades of dedicated searches. Webb's revised picture of the Milky Way carries profound implications for understanding the dark matter halo that envelops our galaxy, and those implications suggest the invisible component may be even more substantial than previous models calculated. The history of dark matter discovery stretches back nearly a century, to the 1930s, when Swiss astronomer Fritz Zwicky studied the Coma cluster of galaxies and noticed something deeply puzzling. The galaxies within the cluster moved too fast, far too fast, to be held together by the gravitational attraction of their visible mass. By Zwicky's calculations, the cluster should have flown apart long ago, unless some unseen material provided additional gravitational glue. He coined the term dunkle Materie, German for dark matter, and proposed that invisible mass pervaded the cluster. His contemporaries largely ignored him, partly because the observations were difficult to verify, and partly because Zwicky had a prickly personality that made collaboration difficult. The evidence accumulated regardless of whether astronomers wanted to believe it. By the 1970s, Vera Rubin and Kent Ford had measured the rotation curves of spiral galaxies with sufficient precision to demonstrate that stars in the outer regions orbited far faster than visible mass distributions could explain. Either Newton's laws of gravity broke down at galactic scales, a possibility some physicists still explore, or invisible mass surrounded every galaxy in quantities exceeding the visible stars and gas by factors of 5 or more. The dark matter hypothesis eventually won acceptance, though the particle nature of this substance remained unknown despite enormous experimental efforts to detect it directly. The Milky Way possesses its own dark matter halo, a roughly spherical distribution of invisible mass extending well beyond the visible disk and bulge. Traditional estimates suggested this halo contained roughly 1 trillion solar masses of dark matter, making it the dominant component of our galaxy by far. The visible stars, gas and dust that constitute everything we can actually see amount to perhaps 200 billion solar masses, a small fraction of the total. We live in a dark matter galaxy with a thin frosting of luminous material on top. Webb's observations revise this picture upward in ways that continue to provoke scientific debate. The logic proceeds through several steps, each involving careful measurement and sophisticated modelling. First, Webb reveals stellar populations at greater distances than previous surveys detected, extending the known galactic disk and halo further into space. Second, these distant stars move with particular velocities that can be measured through spectroscopic observations of their light. Third, those velocities constrain the gravitational potential they orbit within, which depends on the total mass enclosed within their orbital radii. Fourth, since the visible mass at these distances is minimal, most of that enclosed mass must be dark matter. The preliminary analyses suggest the Milky Way's dark matter halo may contain closer to 1.5 trillion solar masses, roughly 50% more than earlier estimates. This upward revision comes with substantial uncertainty, as scientists still argue about systematic errors in the distance and velocity measurements, alternative interpretations of the data, and potential modifications to gravitational theory that might reduce the inferred dark matter content. But the trend across multiple independent analyses points consistently toward a more massive halo than previous models described. Here is the quirky detail that makes dark matter research simultaneously frustrating and fascinating. Despite knowing that dark matter dominates the galaxy's mass budget, astronomers cannot point to a single confirmed dark matter particle. Numerous candidates have been proposed, from weakly interacting massive particles called WIMPs to ultralight axions to primordial black holes, and enormous experiments have searched for direct detection signals without success. The particle might be something theorists have not yet imagined, or it might not be a particle at all in the conventional sense. What we know with confidence is that something provides the gravitational scaffolding galaxies require to hold together, and that something exceeds visible matter by roughly 5 to 1. The distribution of dark matter within the halo also carries information Webb helps constrain. Theoretical models predict that dark matter should concentrate toward the galactic center, forming a dense core or cusp depending on the particle's properties. Observational attempts to measure this central density have produced conflicting results, with some studies favoring steep cusps and others suggesting flattened cores. The stellar populations Webb detects in the inner galaxy provide new constraints on this long-standing debate, though consensus remains elusive. Scientists still argue about whether the Milky Way's dark matter halo is smooth or clumpy, uniform or structured by subhalos left over from the galaxy's hierarchical assembly. Cold dark matter models predict substantial substructure, with the main halo containing thousands of smaller dark matter concentrations, miniature halos that never accumulated enough gas to form visible stars. Warm dark matter models predict smoother distributions with less small-scale structure. Webb cannot directly image dark matter subhalos, obviously, but the stellar streams and tidal features it reveals in the outer galaxy bear signatures of gravitational perturbations that constrain substructure models. The practical implications of a more massive dark matter halo extend beyond academic curiosity. The Milky Way's total mass determines its gravitational influence on neighbouring galaxies, its place in the local group hierarchy, and the dynamics of its eventual merger with Andromeda. A 50% upward revision in dark matter mass makes our galaxy significantly more gravitationally dominant than previous estimates suggested, potentially affecting calculations of everything from dwarf galaxy orbits to the predicted morphology of the post-merger Milky system. You rest there, cradled by invisible mass, your body held to Earth by gravity, while Earth orbits a sun held to the galaxy by forces transmitted through dark matter's unseen architecture. The Milky Way you see on clear nights represents perhaps 15% of your galactic home's total mass. The rest surrounds you invisibly, detectable only through its patient gravitational embrace, revealed now more clearly than ever before by a telescope that sees light your eyes cannot perceive, mapping structures your intuition cannot grasp. The hidden architecture extends further than we knew, more massive than we calculated, the silent majority of a galaxy only beginning to reveal its true scale. Ancient relics at the edge of the galaxy await your attention now, those venerable stellar survivors that formed when the universe itself was young, when the first light emerged from primordial darkness and matter began its long journey toward complexity. Webb has detected stars in the Milky Way's outer halo whose ages approach the age of the universe itself, objects that have burned steadily for over 13 billion years, while generations of younger stars formed, lived, and died around them. These ancient relics carry in their chemical compositions the signatures of cosmic epochs we can study no other way. The oldest stars in the Milky Way belong to a population astronomers call Population 2, a term dating to Walter Bayard's classification scheme from the 1940s. Population 2 stars contain very few heavy elements, metals in astronomical parlance, because they formed before successive generations of stellar nucleosynthesis had enriched the interstellar medium with elements heavier than hydrogen and helium. The Big Bang produced only the lightest elements, and everything heavier, the carbon in your cells, the oxygen you breathe, the iron in your blood, required stellar furnaces to forge. Population 2 stars formed from nearly pristine primordial gas before much stellar processing had occurred, and their metal-poor compositions mark them as relics of that early epoch. Webb's infrared sensitivity allows detection of these faint ancient stars at distances previous instruments could not reach. The outer galactic halo, that diffuse sphere of stellar material surrounding the disk, contains disproportionate numbers of Population 2 objects, survivors from the Milky Way's earliest assembly phases. Many appear to have formed in small protogalactic fragments that later merged to build the larger structure we inhabit today. Their chemical signatures preserve information about nucleosynthesis in the first generation of stars, objects that formed and died before any currently observable star came into existence. The historical search for the oldest stars in the Milky Way began in earnest during the 1950s and 1960s, when astronomers developed spectroscopic techniques capable of measuring stellar metal abundances with reasonable precision. Each discovery of an extremely metal-poor star pushed the boundary of known cosmic archaeology further back in time. By the 2000s, surveys had identified stars with iron abundances less than 100,000th of the Sun's, objects that must have formed when the universe was less than a few 100 million years old. These discoveries challenged theoretical models of early star formation and provided constraints on conditions in the primordial universe that no other observations could supply. Webb extends this archaeological survey into previously inaccessible regions of the outer halo, where the most ancient stars preferentially reside. The detection of additional extremely metal-poor stars at great distances from the galactic centre provides new data points for understanding how the Milky Way assembled from smaller fragments during its early history. Each ancient relic carries slightly different chemical signatures depending on exactly which nucleosynthetic processes contributed to the gas cloud from which it formed, and comparing these signatures across large samples constrains models of early stellar populations and their explosive deaths. Here is the quirky detail that makes these ancient stars particularly poignant. They have witnessed the entire history of the Milky Way unfolding around them. When these objects formed, the galaxy did not exist in its current form. There was no spiral structure, no organized disk, merely chaotic aggregations of gas and small stellar systems beginning to fall together under gravitational attraction. These stars orbited through the growing galaxy as it cannibalized neighbors, as spiral arms developed and dissolved and reformed, as billions of years of cosmic evolution transformed a primordial mess into the majestic pinwheel we see today. If stellar consciousness existed, these ancient witnesses would have stories to tell that dwarf anything in human experience. Scientists still argue about the ages of the oldest Milky Way stars and how those ages compare to the universe's total age, currently estimated at approximately 13.8 billion years. Some extremely metal-poor stars appear to have ages of 13.5 billion years or more, leaving remarkably little time between the Big Bang and their formation. This near simultaneity challenges models that require substantial time for the first stellar generation to form, process heavy elements through supernova, and seed the gas from which population 2 stars formed. Either the first stars formed and died faster than some models suggest, or the age estimates for these ancient objects carry larger uncertainties than often acknowledged. The spatial distribution of ancient stars provides additional constraints on galactic assembly models. Webb reveals these relics scattered throughout the outer halo at distances exceeding 100,000 light-years from the galactic centre, far beyond the visible disk. Their orbits tend to be highly elliptical, diving through the inner galaxy before retreating to the sparse outer regions, consistent with formation in small fragments that later merged into the growing Milky Way. The halo population is not uniform but shows evidence of streams and structures, the gravitationally shredded remnants of ancient mergers still visible after billions of years of orbital evolution. The chemical archaeology Webb enables represents one of astronomy's most powerful techniques for studying epochs no telescope can directly observe. The first generation of stars, population 3 objects composed purely of primordial hydrogen and helium, have never been directly detected. They are believed to have been massive, short-lived, and completely absent from the present-day universe. but their nucleosynthetic products survive in the second-generation stars that formed from gas enriched by their explosive deaths. By analysing the chemical abundances of extremely metal-poor population 2 stars, astronomers indirectly constrain the properties of those never-observed population 3 progenitors. You lie there contemplating light that left ancient stars when the universe was barely 1 billion years old, photons that have travelled for most of cosmic history to reach instruments sensitive enough to detect them. The Milky Way's outer reaches contain objects older than Earth, older than the Sun, older than the geological history of any world we know. These patient survivors glow faintly at the galaxy's edge, witnesses to eternity, their existence revealed now by infrared eyes peering through veils of dust and distance. The relics endure, and through them, the universe's earliest epochs speak to anyone willing to listen across the vast silence of space and time. The metallicity gradient Webb traces through the Milky Way tells a complementary story of galactic chemical evolution. Stars closer to the galactic centre tend to be more metal-rich, formed from gas that experienced many generations of stellar enrichment. Stars in the outer disk and halo tend to be more metal-poor, formed earlier or from less processed material. This gradient was known before Webb, but the new observations extend it to greater distances and reveal substructures within the overall trend that encode information about the galaxy's assembly history, the timing of merger events, and the efficiency of mixing processes that redistribute chemically enriched gas throughout the galactic volume. The galactic centre's crowded chaos now demands your attention. That dense and violent region where stars swarm around a supermassive black hole, like moths around a flame of unimaginable proportions. You descend now from the serene outer halo toward the very heart of the Milky Way, where Webb's infrared vision has revealed thousands of previously unknown objects orbiting the gravitational monster designated Sagittarius A star. This is the most extreme environment in our galaxy, a place where stellar density exceeds anything in the solar neighbourhood by factors of millions, where tidal forces can shred unwary stars, and where the rules governing stellar dynamics become exotic beyond everyday imagination. Sagittarius A star, the supermassive black hole at the Milky Way's centre, contains approximately 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sun. This fact alone should give you pause. 4 million times the mass of an ordinary star, concentrated so intensely that not even light can escape its gravitational clutches. The event horizon, that boundary beyond which escape becomes impossible, stretches roughly 15 million miles across, and around this boundary, a population of stars executes breathtaking orbital dances at velocities that would make any orbital mechanics textbook weep. The historical discovery of Sagittarius A star unfolded gradually during the late 20th century, driven primarily by radio observations that could penetrate the dense dust obscuring the galactic centre from optical telescopes. In 1974, astronomers Bruce Ballack and Robert Brown detected a compact radio source at the galaxy's dynamic centre, an object that would eventually be confirmed as the supermassive black hole theorized to lurk at the hearts of most large galaxies. By the 1990s and 2000s, infrared observations has tracked individual stars orbiting this unseen mass, their trajectories providing some of the most convincing evidence for black hole existence available anywhere in the universe. Webb builds upon this infrared legacy with instruments vastly more sensitive and resolving than their predecessors. The central parsec of the Milky Way, the innermost few light-years around Sagittarius A star, was already known to contain a dense star cluster and numerous unusual objects. But Webb's observations have revealed thousands of additional sources in this region, objects too faint or too deeply embedded in dust for earlier instruments to detect. Some appear to be ordinary stars in extraordinary environments. Others defy easy classification, their spectral signatures suggesting exotic compositions or evolutionary states found nowhere else in the galaxy. The stellar population surrounding the supermassive black hole includes some genuine oddities that scientists continue debating. The so-called S-stars, a group of young, massive objects orbiting within fractions of a light-year from the black hole, pose particular puzzles. Star formation theory struggles to explain how such massive stars could form in the extreme tidal environment near a supermassive black hole, where gravitational stresses should prevent gas clouds from collapsing. Either these stars formed elsewhere and migrated inward through complex dynamical processes, or star formation physics works differently than current models describe in extreme environments. Webb's detection of additional young stars near the galactic centre intensifies this debate without resolving it. Here is the quirky detail that captures the extremity of this environment. Some stars near Sagittarius A star orbit so rapidly that they complete full circuits in only 15 years or less. By contrast, the Sun requires roughly 230 million years to complete a single orbit around the galactic centre. These hypervelocity inner stars experience gravitational accelerations millions of times stronger than anything in the solar neighbourhood, and their orbital parameters can shift measurably over human timescales. Astronomers have tracked the same individual stars through significant fractions of their orbits, watching them arc around the invisible black hole in real time, the only place in the universe where orbital motion around a supermassive black hole can be directly observed. The infrared data Webb provides also reveals complex structures of gas and dust in the central region, material that may eventually feed the black hole's appetite. Sagittarius A star is currently in a quiet phase, accreting relatively little material and therefore producing minimal radiation compared to the active galactic nuclei seen in other galaxies. But the gas structures Webb observes suggest this quietude may not persist indefinitely. Filaments and streamers of material spiral toward the central region, potential future fuel for accretion episodes that could dramatically brighten the galactic centre in coming millennia. Scientists still argue about the history of activity at the Milky Way's centre, and whether major accretion events occurred in the astronomically recent past. X-ray observations have detected structures called the Fermi bubbles, enormous lobes of hot gas extending tens of thousands of light-years above and below the galactic plane, possibly inflated by powerful jets from an active phase of Sagittarius A star within the past few million years. If true, the currently dormant black hole was recently much more violent, and Webb's observations of the central environment provide context for understanding what triggered that activity and whether similar episodes might recur. The density of objects in the galactic centre creates gravitational dynamics unlike anywhere else in the Milky Way. Stars interact frequently through close passages, potentially exchanging orbital energy in ways that can either eject objects from the region entirely or capture them into ever tighter orbits around the black hole. Some hypervelocity stars discovered in the outer galaxy are thought to have originated from this central chaos, gravitationally slingshot outward by encounters near Sagittarius A star at velocities exceeding the galaxy's escape speed. Webb's census of the central stellar population helps constrain models of these ejection processes. You drift through the conceptual density of this crowded stellar metropolis, where millions of stars occupy a volume the Sun's neighbourhood would consider impossibly cramped. The supermassive black hole sits silently at the centre, patient and eternal, its presence revealed only through the frantic motions of everything orbiting around it. Webb watches this chaos with infrared eyes that cut through the dust, cataloguing objects that will spend their entire existence dancing around gravity's ultimate expression, never to be seen by human eyes but now known to science through the patient accumulation of infrared photons gathered by a golden mirror floating at the edge of Earth's gravity well. The proper motion studies Webb enables in the galactic center region deserve particular mention as you settle further into the darkness. By observing the same stellar fields multiple times over months and years, astronomers can measure how individual stars move across the sky, their proper motions revealing three-dimensional orbital trajectories when combined with radial velocity measurements from spectroscopy. This technique has already produced stunning results from earlier infrared observatories, but Webb's superior resolution allows tracking of fainter and more numerous objects than ever before. The resulting orbital catalogues will constrain the mass distribution near the central black hole with unprecedented precision, potentially revealing the presence of smaller black holes or other massive objects hidden within the crowded stellar swarm. Spiral arms are more complex than traditional models suggested, and as you drift outward from the chaotic galactic center, you enter the grand architectural features that give the Milky Way its characteristic pinwheel shape. These luminous arms, sweeping gracefully around the galactic center like the vanes of a cosmic windmill, have captured human imagination since astronomers first recognized our galaxy's spiral structure. But Webb reveals that what appeared as smooth, elegant curves in earlier observations actually harbor intricate substructures, spurs, feathers, and stellar nurseries more numerous and varied than previous maps indicated. The history of mapping the Milky Way's spiral structure represents one of astronomy's more challenging endeavours, complicated by our unfortunate position embedded within the very disk we are trying to map. It is genuinely difficult to see the forest for the trees when you're standing among the trees, and our solar system's location in the galactic plane means we view the spiral arms edge-on, foreshortened and partially obscured by the very dust and gas that makes them visible in the first place. For most of the 20th century, astronomers debated how many spiral arms the Milky Way possessed, where exactly they were located, and whether our galaxy was a grand design spiral with two dominant arms or a flocculent spiral with many fragmentary arm segments. The emerging consensus, shaped by decades of radio, infrared, and optical observations culminating in Webb's contributions, describes a four-arm spiral pattern with substantial additional structure. The major arms, given names like Perseus, Sagittarius Carina, Scutum Centaurus and Norma, wind outward from the central bar in logarithmic spirals, their luminosity dominated by young, massive stars and the glowing nebulae where new stars form. Between and alongside these major arms, numerous minor arms, spurs and interarm structures create a complexity that simple models fail to capture. Webb's infrared observations reveal this complexity with unprecedented clarity. The dust that pervades the spiral arms, simultaneously their glory and their obscuration, becomes transparent to Webb's instruments, allowing detection of stellar populations hidden within the densest arm regions. Young stellar objects still embedded in their natal clouds become visible. Evolved stars that optical surveys could not place accurately now populate detailed three-dimensional maps. The spiral pattern emerges not as a smooth, idealized form, but as a living, turbulent structure shaped by gravitational dynamics, star formation feedback, and the ongoing consumption of gas from the intergalactic medium. The solar system resides in a minor structure called the Orion's spur, sometimes classified as an arm and sometimes as merely a bridge between major arms, depending on how generously one draws the boundaries. This location between the Sagittarius and Perseus arms provides reasonably clear lines of sight in certain directions while placing dense arm regions in others. Webb's ability to see through intervening material has significantly improved maps of arm regions that lie beyond intervening dust lanes from the Sun's perspective. Here is the quirky detail that makes spiral arm physics particularly interesting. The arms are not physical objects moving through the galaxy like the spokes of a wheel. Rather, they are density waves, patterns of enhanced stellar and gas density that propagate through the galactic disk like waves across water. Individual stars pass through the arms as they orbit the galactic center, slowing slightly in the denser regions before speeding up as they exit. The arms persist not because the same material always composes them, but because the density pattern itself rotates at a different rate than the stellar population, creating a standing wave structure. Stars are born in the arms because gas compression triggers star formation, and the brightest young stars die before leaving the arms, making the arms appear more luminous than the interarm regions. Scientists still argue about the detailed dynamics driving spiral structure, the role of bars in generating and maintaining arm patterns, and whether the Milky Way's arms are long-lived persistent features or transient structures that form, dissolve, and reform on timescales of hundreds of millions of years. Webb cannot resolve these debates directly, but the detailed stellar populations it reveals within and between the arms provide constraints that theoretical models must match. The distribution of stellar ages across arm structures, the chemical abundance gradients along and across arms, and the locations of star-forming regions all carry information about how the spiral pattern interacts with the underlying stellar and gas populations. The bar at the Milky Way's center, that elongated concentration of stars spanning perhaps 10,000 light-years through the galactic bulge, plays a crucial role in spiral dynamics that Webb is helping clarify. Bars can drive density waves that propagate outward and shape spiral arm patterns. They can also channel gas toward the galactic center, potentially fueling episodes of star formation or black hole activity. The bar's extent, orientation, and stellar population were poorly constrained by optical observations, but Webb's infrared sensitivity reveals the structure in detail, showing a complex three-dimensional shape that older models oversimplified. The star-forming regions within spiral arms have received particular attention from Webb observers, and the images are genuinely breathtaking even in scientific contexts. Pillars of gas and dust, illuminated by newborn stars, stretch across light-year scales. Protoplanetary disks orbit infant stars, potential future solar systems caught in the act of formation. Jets of material blast outward from stellar embryos, shocking the surrounding medium and triggering chain reactions of additional star formation. These images have graced magazine covers and social media feeds, but they also represent scientific data that constrains models of how stars form, how planets assemble, and how spiral arm dynamics influence these processes. You recline into the knowledge that the galaxy's visible structure is far more intricate than the simple diagrams you might have seen in textbooks. The spiral arms wave and branch and feather, populated by stellar nurseries and ancient wanderers alike, shaped by gravitational dynamics that operate on timescales our individual lives cannot perceive. Webb reveals this complexity one infrared photon at a time, building a picture of a galaxy that defies simplification, that rewards deeper observation with ever more detailed structure, that remains fundamentally surprising even after centuries of astronomical study. Satellite galaxies and galactic cannibalism enter your awareness now, as the Milky Way reveals itself not as an isolated island universe, but as the dominant member of a cosmic family, a gravitational patriarch surrounded by dozens of smaller companions that it has been steadily devouring across billions of years. Webb's observations have deepened our understanding of this ongoing feast, revealing evidence that our galaxy grew to its current size partly by consuming smaller neighbours, absorbing their stars and dark matter into an ever-expanding structure that continues to cannibalize even today. The large and small Magellanic Clouds, visible to naked eyes from southern latitudes, represent the Milky Way's most prominent satellite galaxies. These irregular dwarf galaxies orbit our own at distances of roughly 160 and 200,000 light-years respectively, close enough that gravitational interactions have visibly distorted their shapes, and stripped streams of gas that stretch across the southern sky. Ancient peoples in the southern hemisphere wove stories around these luminous patches, and Magellan's circumnavigation brought them to European astronomical attention in the 16th century. But the Magellanic Clouds represent only the largest members of a much more numerous satellite population. Current surveys have identified over 60 dwarf galaxies orbiting the Milky Way, with more discovered regularly as instruments improve. These range from relatively substantial systems containing millions of stars down to ultra-faint dwarfs, with stellar populations smaller than some globular clusters. Many lie hidden behind the Milky Way's disk as seen from Earth, detectable only through dedicated surveys that peer through the galactic plane's dusty obscuration. Webb's infrared capabilities have contributed to the discovery and characterization of these faint companions, revealing stellar populations and structural details that optical surveys missed. The historical understanding of dwarf galaxy populations evolved dramatically over the past few decades. In the 1990s, astronomers knew of perhaps a dozen Milky Way satellites. The count increased steadily through the 2000s as digital sky surveys became sensitive enough to detect ultra-faint systems. Each new discovery raised questions about how many more remained hidden, leading to the so-called missing satellites problem. Cold dark matter simulations predicted far more dwarf galaxy halos orbiting the Milky Way than observed satellite galaxies existed. Either the simulations were wrong, or most small dark matter halos failed to form visible stellar populations, or many satellites remained undetected. Webb's discoveries and refined characterizations of known satellites suggest that observational incompleteness accounts for at least part of the missing satellite discrepancy. Ultra-faint dwarfs are genuinely difficult to detect. Their sparse stellar populations lost against the foreground of Milky Way stars unless observers know exactly where to look. The infrared sensitivity that allows Webb to see through galactic dust also improves detection of intrinsically faint stellar systems, and the census continues to grow as observations accumulate. Here is the quirky detail that makes the satellite population particularly fascinating. Many of these dwarf galaxies are not long for this cosmic world. Gravitational tides from the Milky Way are actively stripping stars from several satellites, stretching them into elongated stellar streams that will eventually merge completely into the main galaxy's halo. The Sagittarius dwarf elliptical galaxy, discovered in 1994 and located behind the galactic center as seen from Earth, provides the most dramatic example. This system has already passed through the Milky Way's disk multiple times, losing substantial stellar material with each passage, and now wraps nearly completely around our galaxy in tidal streams, visible across much of the sky. Scientists still argue about exactly how many satellites the Milky Way has consumed throughout its history, and how much of the galaxy's current mass came from accreted dwarf systems versus in situ star formation. The stellar streams Webb helps trace provide crucial evidence for this cosmic archaeology. Each stream preserves information about its parent dwarf galaxy. The chemical abundances reveal stellar populations, the orbital dynamics reveal merger timing, and the stream morphology reveals the gravitational potential through which it orbits. By studying multiple streams simultaneously, astronomers reconstruct the Milky Way's dining history, learning which courses were consumed when, and how substantially each contributed to the final meal. The dark matter content of satellite galaxies provides particularly important cosmological constraints. Dwarf galaxies are believed to be some of the most dark matter-dominated systems in the universe, with mass to light ratios far exceeding those of large galaxies. Measuring the stellar velocities within these small systems reveals their gravitational potentials and hence their total masses, and comparisons with visible matter content indicate dark matter contributions of 90% or more in many cases. Webb's observations of stellar populations in ultra-faint dwarfs improve velocity measurements and mass estimates for these cosmologically important laboratories. The future of the satellite population involves continued absorption into the Milky Way, a process that will reshape the galaxy's outer regions over billions of years. The Magellanic Clouds, despite their current prominence, are likely on their first close approach to the Milky Way, and may not survive as independent systems for another few billion years. Gravitational models suggest they will be tidally disrupted and incorporated into the galactic halo, contributing their stars and gas to the larger structure. The smaller ultra-faint dwarfs face similar fates on shorter timescales, their fragile stellar populations defenseless against tidal forces that grow stronger with each orbit. You contemplate the Milky Way as predator, slowly absorbing its smaller neighbours, growing more massive and complex with each cosmic meal. The galaxy you inhabit is not a static structure but an evolving system, fed by external material that falls inward across billions of years. Webb documents this ongoing buffet, tracking the stellar streams and tidal debris that mark previous consumption events, while monitoring satellites that will constitute future meals. The scale is so vast and the timescales so long that no individual could witness the feeding process, yet the evidence accumulates in archived observations and theoretical models that reconstruct what human lifespans are too brief to perceive directly. The mass problem gets messier with each new Webb observation, as scientists find themselves arguing more vigorously than ever about a question that sounds deceptively simple. Exactly how much does the Milky Way weigh? You might assume that determining the mass of our home galaxy would be a settled matter by now, given centuries of astronomical observation and increasingly sophisticated measurement techniques. But the truth proves more contentious, with different methodologies yielding estimates that span ranges wide enough to make cosmologists uncomfortable, and with Webb's new data adding fuel to debates rather than resolving them. The fundamental challenge lies in measuring mass we cannot see. If the Milky Way contained only visible matter, stars and gas and dust, astronomers could simply add up the luminosity of all detected objects, apply average mass-to-light ratios, and arrive at a total. But as we discussed earlier, dark matter dominates the galactic mass budget by factors of 5 or more, and dark matter reveals itself only through gravitational effects on visible traces. Measuring total mass therefore requires tracking how visible objects move through the galaxy's gravitational potential and inferring the mass distribution responsible for those motions. The rotation curve approach, pioneered by Vera Rubin and colleagues in the 1970s, measures how orbital velocities vary with distance from the galactic center. In a simple model, velocities should decrease at large radii according to Kepler's laws, falling off as the square root of distance. Instead, observed velocities remain roughly constant or even increase slightly into the outer galaxy, indicating that mass extends far beyond the visible disk. By modelling the rotation curve with various dark matter halo profiles, astronomers infer total masses, but the results depend sensitively on assumptions about halo shape, concentration, and extent. An alternative approach uses the motions of satellite galaxies and stellar streams as traces of the Milky Way's gravitational potential at large distances. These objects orbit the galaxy at 100,000 light-year scales, probing regions where the rotation curve becomes difficult to measure directly. The technique is powerful, but complicated by uncertainties in satellite distances, velocities, and the dynamical effects of previous interactions. Different analyses of the same satellite population have yielded mass estimates ranging from roughly 700 billion to over 2 trillion solar masses, a factor of 3 discrepancy that embarrasses a field proud of its precision. Webb's observations contribute to both approaches in ways that have, paradoxically, widened rather than narrowed the disagreements. The extended stellar disk populations Webb detects provide new rotation curve data points at unprecedented distances, but these data prove difficult to interpret consistently. The faint outer disk stars may not occupy circular orbits, as simple rotation curve analyses assume, their motions potentially influenced by recent interactions with satellite galaxies or the asymmetric gravitational effects of the Milky Way's non-spherical halo. Stellar streams Webb helps map provide crucial traces, but their orbital properties reveal tensions between different mass models that resist easy resolution. Here is the quirky detail that captures the essence of the problem. Two independent research groups can analyze essentially the same Webb dataset using different but apparently reasonable assumptions and arrive at mass estimates differing by 50% or more. The error bars on these estimates often fail to overlap, suggesting systematic differences in methodology that exceed random measurement uncertainties. Scientific conferences have featured spirited debates between advocates of higher and lower mass estimates, with neither side able to definitively refute the other's analysis. Scientists still argue about whether the Milky Way is more or less massive than the Andromeda Galaxy, a question with implications for understanding the local group's dynamics and the eventual merger between these two dominant members. Traditional estimates placed Andromeda as the larger system, with a mass roughly 50% greater than the Milky Way. But some recent analyses suggest comparable masses, or even a more massive Milky Way, potentially revising the local galactic hierarchy. The outcome affects predictions for the merger process and the structure of the eventual combined system. The dark matter halo shape adds another layer of complication. Simple models assume spherical halos, but more realistic expectations based on cosmological simulations predict triaxial ellipsoids, flattened or elongated shapes that affect how mass is distributed at different radii. The orientation of a non-spherical halo relative to the disk, the degree of flattening, and the presence of substructure all influence tracer motions in ways that can be misinterpreted if spherical symmetry is incorrectly assumed. Webb's three-dimensional mapping of stellar populations provides constraints on halo shape, but extracting these constraints requires sophisticated modelling that different groups implement differently. The mass enclosed within specific radii matters more for some applications than the poorly constrained total mass. The mass within 50 kiloparsecs, roughly 160,000 light-years, directly affects the orbits of most known satellite galaxies. The mass within the Sun's orbital radius determines local gravitational dynamics. Webb's observations have improved estimates of these intermediate-scale masses, even while total mass estimates remain contentious. The emerging picture describes a galaxy with perhaps 1 trillion solar masses within the inner regions where constraints are strongest, with substantial additional mass at larger radii whose amount remains disputed. You rest with this uncertainty, comfortable perhaps in the knowledge that science does not always provide clean answers, that reality sometimes resists our attempts to quantify it, and that genuine experts can disagree vigorously without either being obviously wrong. The Milky Way weighs somewhere between 700 billion and 2 trillion solar masses, a range that spans nearly a factor of 3, and Webb's magnificent new data have not collapsed that range as much as anyone hoped. The mass problem remains messy, a reminder that our cosmic home still harbours mysteries that sharp instruments and clever analyses cannot immediately resolve. The baryonic mass budget provides somewhat firmer footing, as counting visible matter proves more tractable than inferring invisible dark matter. Webb's stellar population census contributes directly to baryonic mass estimates by identifying stars that previous surveys missed and improving distance measurements for known populations. The emerging picture suggests roughly 50 to 60 billion solar masses in stars, another 10 to 15 billion in interstellar gas, and comparatively negligible contributions from dust and other diffuse material. These visible components represent perhaps 5% of the total mass, with the overwhelming majority residing in the dark matter halo, whose total extent and mass remain the subject of ongoing investigation. The baryon fraction, the ratio of visible to total mass, provides constraints on cosmological models that Webb's observations help refine even as the total mass itself remains contested. Stellar streams tell ghost stories, those ethereal ribbons of stars that trace arcs across the galactic halo, like the fading memories of devoured galaxies. And Webb has mapped these spectral structures in unprecedented detail, revealing narratives of cosmic consumption written in starlight across hundreds of thousands of light years. Each stream represents the gravitationally shredded remnant of a former dwarf galaxy or globular cluster, its stars pulled from their original home and strung along the orbital path like beads from a broken necklace, still moving together but no longer bound, gradually dispersing across eons into the general halo population. The discovery and study of stellar streams began in earnest during the 1990s and 2000s, driven largely by the Sloan Digital Sky Survey's systematic mapping of the northern sky. The Sagittarius stream, associated with the ongoing disruption of the Sagittarius dwarf elliptical galaxy, emerged as the most prominent example, wrapping nearly completely around the Milky Way in a vast polar orbit. Additional streams followed. The Orphan Stream, GD1, Palomar 5, and dozens of others with names and catalogue numbers that accumulate in astronomical databases. Each stream carries information about its progenitor system and, crucially, about the gravitational potential through which it orbits. Webb's contributions to stream studies come primarily through detecting fainter stellar populations along known streams and revealing new streams that escape detection by shallower surveys. The telescope's infrared sensitivity proves particularly valuable for streams that pass behind the dusty galactic disk as seen from Earth, regions where optical surveys lose sensitivity dramatically. Several streams known only from fragmentary detections now show continuous structure in Webb observations, their full extents finally revealed after years of partial glimpses. The physics of stream formation makes these structures powerful probes of galactic dynamics. When a small stellar system enters the Milky Way's gravitational influence, tidal forces begin stretching it along its orbital direction. Stars slightly ahead of the system's center gain orbital energy and drift forward. Stars slightly behind lose energy and fall back. The result is an elongating stream that traces the progenitor's orbital path with remarkable fidelity. The stream's morphology, its width, gaps, density variations, and kinks all carry information about the gravitational field it traverses. Here is the quirky detail that makes stream studies particularly exciting. The streams are sensitive to gravitational perturbations from dark matter substructure that would otherwise be invisible. Cold dark matter models predict that the Milky Way's halo should contain thousands of dark matter subhalos, concentrations of invisible matter left over from the galaxy's hierarchical assembly. Most of these subhalos never accumulated enough gas to form visible stars, making them completely undetectable through conventional means. But if a dark matter subhalo passes near a stellar stream, its gravity will perturb the stream's stars, creating gaps, kinks, or density variations that persist along the stream's length. Scientists still argue about whether the observed stream morphologies require significant dark matter substructure or can be explained by other effects, including passage through the galactic disk, interactions with giant molecular clouds, or internal dynamics of the progenitor systems. Webb's detailed stream mapping provides the data needed to distinguish between these possibilities, though interpreting that data requires sophisticated simulations and careful statistical analysis. The jury remains out on whether streams have definitively detected dark matter subhalos, but the technique remains among the most promising methods for probing invisible matter distribution. The chemical abundances of stream stars provide another window into galactic archaeology. Stars within a single stream share common chemical signatures inherited from their parent system, distinct from the general halo population's mixed composition. By measuring these abundances for large samples of stream stars, astronomers characterize the progenitor dwarf galaxies that no longer exist as coherent systems. The Milky Way's halo becomes a museum of consumed companions, their stellar collections dispersed but still identifiable through careful chemical forensics. The ages of streams vary enormously, from the relatively young Sagittarius stream whose progenitor remains partially intact, to ancient structures whose progenitors were consumed so long ago that the streams themselves have begun dispersing into the smooth halo background. Detecting these older, more diffuse structures requires exactly the kind of deep, wide-field infrared observations Webb provides. The oldest streams may preserve information about very early accretion events, when the young Milky Way was first building its halo from infalling protogalactic fragments. The three-dimensional structure of streams has improved dramatically with Gaia's proper motion measurements combined with Webb's deep photometry. Knowing not just where stars appear on the sky, but how they move across it allows reconstruction of full orbital paths, revealing the stream's true spatial configurations rather than merely their projections. Some streams that appeared simple in two-dimensional views turn out to have complex three-dimensional structures, multiple wraps around the galaxy, or interactions between different streams that create confusing overlapping patterns. You drift along these ghostly stellar rivers, following the memories of galaxies that ceased to exist as independent entities millions or billions of years ago. Their stars continue orbiting, unaware that the family they once belonged to has been dissolved, still carrying chemical signatures and orbital properties that mark them as immigrants from vanished homes. Webb traces these spectral paths across the darkness, documenting the Milky Way's long history of consumption, reading the ghost stories written in stellar positions and velocities that only instruments of extraordinary sensitivity can perceive. The future evolution of known streams provides insight into the Milky Way's dynamical timescales. Currently coherent streams will gradually disperse as their constituent stars experience differential orbital precession, small variations in orbital period that accumulate over many circuits around the galaxy. Eventually, ancient stream stars will become indistinguishable from the general halo population, their common origin identifiable only through chemical signatures rather than spatial or kinematic clustering. The timescale for this dispersal depends on the stream's orbital properties and the galaxy's gravitational potential, with typical estimates ranging from 1 to 10 billion years for complete mixing. Webb's observations of streams at various evolutionary stages allow calibration of these dispersal processes, connecting the sharp young structures visible today with the smoothly distributed ancient halo populations that represent the endpoint of stream evolution. How we compared Andromeda becomes newly relevant now, as the Milky Way's revised scale changes the cosmic neighborhood's power dynamics in ways that affect everything from local group hierarchy to merger outcome predictions. You find yourself drifting across the 2.5 million light-years that separate our galaxy from the Andromeda Galaxy, also designated M31, the nearest large spiral and our destined collision partner in a few billion years. For decades, astronomers assumed Andromeda was substantially larger and more massive than the Milky Way, the dominant member of our local group of galaxies. Webb's discoveries have complicated this picture. The historical comparison between our galaxy and Andromeda suffered from a fundamental asymmetry. We can see Andromeda from outside, observing its full extent and structure from an external vantage point while we are trapped inside the Milky Way and must infer its properties from our embedded perspective. This asymmetry made Andromeda's dimensions easier to measure directly, and the Milky Way's easier to underestimate. Early size comparisons consistently placed Andromeda as the larger system, with a disk diameter perhaps 50% greater than our own galaxies. Webb's revised picture of the Milky Way narrows this gap considerably. If the Milky Way's disk extends to 200,000 light-years or more, as some Webb analyses suggest, the size differential between the two galaxies essentially disappears. Mass comparisons have proven more contentious, with different measurement techniques yielding conflicting results, as we discussed earlier. Some recent studies suggest the Milky Way might actually be more massive than Andromeda, while others maintain Andromeda's traditional dominance. The true answer likely lies within the overlapping uncertainty ranges of both estimates, making the galaxies more similar in mass than different. The collision between the Milky Way and Andromeda, sometimes called the Milky Way-Andromeda collision, or more playfully Milkomeda, is among the most certain predictions in extragalactic astronomy. The two galaxies approach each other at roughly 250,000 miles per hour, and while some transverse motion complicates trajectory calculations, the eventual merger appears inevitable on timescales of 4 to 5 billion years. The dynamics of this merger depend sensitively on the mass ratio between the two systems, making the revised Milky Way estimates scientifically significant beyond mere cataloguing. Here is the quirky detail that makes the comparison particularly interesting. The merger will not be catastrophic for individual stellar systems like our solar system, despite the dramatic imagery the term collision evokes. The spaces between stars are so vast that direct stellar collisions during the merger will be essentially non-existent. The Sun, if it survives that long, will experience gravitational perturbations that may alter its orbit within the merged galaxy, but it will not collide with Andromeda stars or suffer any physical damage from the merger process. The real drama occurs on galactic scales. As the spiral structures of both galaxies are disrupted, gas is compressed to trigger starbursts, and the combined system eventually relaxes into an elliptical galaxy, lacking the graceful spiral arms of its parent systems. Scientists still argue about the detailed timeline and dynamics of the Milky Way-Andromeda merger, with simulations yielding somewhat different outcomes depending on initial conditions and mass assumptions. A more massive Milky Way would make the merger more symmetric, with neither galaxy clearly dominating the dynamics. The resulting elliptical system would inherit properties from both parents more equally, rather than bearing Andromeda's imprint more strongly as earlier simulations suggested. The Triangulum galaxy, M33, a smaller spiral companion to Andromeda, may also participate in the merger, adding further complexity to predictions. The local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller systems, derives its structure from the masses and positions of its dominant members. If the Milky Way proves more massive than previously thought, its gravitational influence extends further and affects more of the local group's dynamics. Dwarf galaxy orbits, the timing of future interactions, and the eventual fate of the entire grouping all depend on mass distributions that Webb's observations help constrain. The approach of Andromeda is already producing observable effects on both galaxies. Tidal interactions have likely influenced the dynamics of both systems' outer regions, and the gas halos surrounding each galaxy may already be in contact, mixing across the intergalactic void. Webb's ability to detect faint structures in galactic outskirts provides tools for studying these preliminary interactions, though the effects remain subtle compared to the dramatic transformation that awaits in billions of years. You contemplate the distant future when a collision that began billions of years ago reaches its conclusion and the night sky of whatever world you might imagine observing from transforms utterly. The graceful spiral arms dissolve into a smooth elliptical glow. The Milky Way's familiar band across summer skies gives way to an amorphous luminous fog. New stars form in the compressed gas where the galaxies interpenetrate, a final burst of stellar creation before the merged system settles into quiescence. The revision of our galaxy's scale does not change this ultimate fate, merely adjust the terms of engagement between gravitational titans destined to become one. The comparison with Andromeda extends to other properties beyond size and mass. Both galaxies possess central supermassive black holes that will eventually spiral together and merge, releasing gravitational waves detectable across cosmic distances. Both galaxies host populations of satellite dwarf galaxies that will participate in the combined system's dynamics. Both galaxies contain ancient stellar populations dating back to near the universe's birth, and young stars forming in spiral arms today. The similarities exceed the differences, making the Milky Way and Andromeda more like siblings than distant cousins in the cosmic family tree. The spectroscopic comparisons between Milky Way and Andromeda stellar populations reveal both similarities and intriguing differences that Webb is helping characterize. Andromeda appears to host a larger population of metal-rich stars in its halo than the Milky Way, suggesting a more extensive history of consuming relatively massive satellite galaxies that had undergone substantial internal chemical enrichment. This difference in merger history manifests in observable properties that constrain models of how each galaxy assembled over cosmic time. Webb's ability to obtain spectra of faint stars in the Milky Way's outer halo allows increasingly detailed comparisons with Andromeda's better-studied outer regions, revealing whether the apparent differences represent genuine distinct assembly histories or merely artifacts of different observational depths and techniques. The bar structures in both galaxies also merit comparison, as bars influence spiral arm dynamics, gas flow toward galactic centers, and potentially black hole feeding rates. The Milky Way's bar appears more prominent relative to its disk than Andromeda's, suggesting different evolutionary histories or current dynamical states. Webb's infrared observations of the Milky Way's bar provide the detailed structural measurements needed for meaningful comparison with Andromeda's bar properties derived from external observations. Understanding how and why these bars differ helps constrain general theories of bar formation and evolution in spiral galaxies. The habitable zone expands dramatically when you consider the implications of a larger galaxy containing more stars than previous estimates acknowledged. You drift now through the cosmic real estate market, surveying planets and possibilities across a stellar population that may approach 500 billion suns, each potentially hosting worlds where conditions might favour the emergence of life. The Milky Way's revised scale does not merely satisfy astronomical curiosity, but carries profound implications for astrobiology and the search for life beyond Earth. The concept of habitable zones, sometimes called Goldilocks zones, refers to the regions around stars where liquid water could exist on planetary surfaces. Water, as far as we understand biochemistry, provides the universal solvent within which life's molecular machinery operates. Too close to a star, water boils away. Too far, water freezes solid. The habitable zone represents that just right orbital distance where moderate temperatures allow water to remain liquid, and every star possesses its own habitable zone, whose boundaries depend on the star's luminosity and spectral type. The statistical extension from stellar populations to potentially habitable planets proceeds through several steps, each carrying uncertainties that accumulate into wide ranges of final estimates. First, Webb's revised stellar census suggests the Milky Way contains roughly 500 billion stars, rather than the 200 to 400 billion previous estimates quoted. Second, Exoplanet surveys suggest that roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone, with different ratios for other stellar types. Third, not all planets in habitable zones will actually be habitable, as atmospheric composition, magnetic field strength, geological activity, and numerous other factors influence whether surface conditions actually support liquid water. Multiplying through these factors with Webb's revised stellar populations yields estimates of tens of billions of potentially habitable planets in the Milky Way, substantially higher than earlier calculations based on smaller stellar counts. The number sounds almost absurdly large, difficult to reconcile with the apparent absence of any evidence for extraterrestrial life despite decades of searching. This tension, often called the Fermi paradox, after physicist Enrico Fermi's famous lunch table question about why we have not detected aliens if they should be so numerous, grows more acute as the estimated number of potential habitats increases. Here is the quirky detail that makes habitable zone calculations particularly interesting. Red dwarf stars, which Webb excels at detecting and which comprise the majority of the stellar population, host habitable zones very close to their surfaces. Planets in these zones orbit their stars in days or weeks rather than years, experiencing gravitational tidal effects that may lock one hemisphere permanently facing the star. Whether such tidally locked worlds can support life remains hotly debated, with arguments both for and against their habitability appearing in the scientific literature. If red dwarf planets prove generally habitable, the number of potential life-hosting worlds increases enormously. If they prove generally sterile, the number drops substantially, but remains impressively large. Scientists still argue about how to properly define habitable zones and whether the concept meaningfully constrains the distribution of potential life. Some astrobiologists advocate for broader definitions that include subsurface oceans like those suspected on Europa and Enceladus, worlds that would be considered frozen wastelands by traditional habitable zone criteria. Others suggest that atmospheric effects can extend habitable conditions to orbital distances both closer and farther from stars than simple calculations suggest. The disagreements reflect genuine scientific uncertainty about what conditions life requires, uncertainty that only direct detection of extraterrestrial biology could resolve. Webb's contributions to habitability studies extend beyond mere star counting to include direct characterization of exoplanet atmospheres. The telescope's spectroscopic capabilities allow detection of atmospheric molecules on planets transiting across their host stars, and the resulting data constrains atmospheric compositions in ways relevant to habitability assessments. Early Webb observations have detected water vapor, carbon dioxide, and other molecules in exoplanet atmospheres, demonstrating the feasibility of searching for biosignatures, chemical signs of life, on potentially habitable worlds. The galactic habitable zone concept extends the planetary habitable zone idea to larger scales, identifying regions of the Milky Way where conditions might favour life-bearing planets. The inner galaxy, with its high stellar density and frequent supernovae, may be too hazardous for life to persist, with radiation events sterilizing planets before complex organisms can evolve. The outer galaxy, with its low metallicity and sparse stellar populations, may lack the heavy elements necessary to form rocky planets. The intermediate region, including the solar neighbourhood, may represent the galactic sweet spot where stars are neither too crowded nor too isolated and where heavy element abundances support planetary geology. Webb's mapping of stellar populations throughout the Milky Way informs galactic habitable zone estimates by revealing how stellar density, age distributions, and chemical compositions vary with position. The extended disk populations Webb detects occupy regions previously considered too sparse to host significant numbers of habitable planets, but the discovery of stars in these zones expands the galactic habitable volume correspondingly. The implications cascade through astrobiological calculations, potentially revising upward the total cosmic real estate where life might take hold. You rest in the comfort of vast possibility, surrounded conceptually by billions of potential habitats scattered across a galaxy far larger than your education suggested. Whether any of those worlds actually host life remains unknown, one of the great unanswered questions that drives astronomical research and captures human imagination. Webb cannot resolve that question directly, but it provides the demographic census upon which probability calculations depend, revealing a Milky Way populous enough that the emergence of life somewhere beyond Earth seems almost inevitable, even if contact or detection remains impractical. The temporal dimension of habitability adds further complexity to these calculations. The Milky Way has existed for roughly 13 billion years, and stars have formed throughout that entire span. Many potentially habitable planets around ancient stars have existed for far longer than Earth, providing time for life to evolve, develop technology, and potentially spread between stars. Other potentially habitable worlds around young stars may not yet have existed long enough for complex life to emerge, even if conditions favour eventual biological development. Webb's ability to estimate stellar ages throughout the galaxy contributes to understanding how the total number of habitats has grown over cosmic time, and what fraction might have existed long enough to host complex biospheres. The expanded stellar census Webb provides applies across all these temporal categories, increasing estimates of both current and historical planetary populations throughout galactic history. Chemical enrichment across the disk tells the story of stellar generations, a narrative written in elemental abundances that Webb reads with unprecedented clarity. You find yourself now immersed in the cosmic recycling system, that grand process by which stars forge heavy elements in their cores and explosively distribute them into the interstellar medium, seeding the raw material from which future stellar generations and their planets form. The Milky Way's chemical composition varies systematically across the disk, and these variations preserve information about billions of years of stellar evolution that Webb's spectroscopic capabilities decode. The Big Bang produced essentially only hydrogen, helium, and trace amounts of lithium. Every heavier element, everything from carbon and oxygen to iron and uranium, required stellar nuclear synthesis to create. The first generation of stars, those hypothetical population 3 objects that have never been directly observed, forged elements up to iron in their cores through nuclear fusion. When they exploded as supernovae, they scattered these newly created elements into surrounding space, slightly enriching the gas from which the next stellar generation would form. This process repeated through cosmic time, each generation of stars producing and dispersing heavier elements, gradually increasing the metallicity of the interstellar medium. The historical understanding of galactic chemical evolution developed through decades of spectroscopic surveys that measured elemental abundances in stars at various locations and ages. A clear pattern emerged. Younger stars and stars closer to the galactic centre tend to have higher metallicities than older stars and stars in the outer disk or halo. This gradient makes sense given that the inner galaxy formed stars more actively and recycled material more efficiently than the sparse outer regions. But the detailed shape of the gradient, its variation with time and position, and the scatter around mean trends all carry information about star formation history, gas flows, and mixing processes that simple models fail to capture. Webb's spectroscopic capabilities extend chemical evolution studies to stellar populations. Previous instruments could not analyze in sufficient numbers. The faint outer disk stars Webb detects, the ancient halo populations, and the dust-obscured inner galaxy regions all become accessible to abundance measurements. The resulting data reveal chemical gradients more complex than earlier surveys suggested, with substructures and variations that encode information about the galaxy's assembly history, the timing of merger events, and the efficiency of gas mixing across different galactic epochs. Here's the quirky detail that makes chemical evolution studies particularly informative. Different elements carry different information because they are produced by different processes. Carbon and oxygen come primarily from intermediate mass stars that die as planetary nebulae, while heavier elements like iron come largely from explosive supernovae. The ratio of these element abundances reveals the relative contributions of different stellar populations to the gas from which a given star formed. By measuring multiple elemental ratios for many stars, astronomers reconstruct not just overall metallicity trends, but the detailed history of which types of stars dominated at different times and locations. Scientists still argue about the details of chemical evolution models, including how efficiently the Milky Way accreted metal-poor gas from the intergalactic medium, how rapidly newly synthesized elements mixed into the general interstellar medium, and how mergers with dwarf galaxies introduce stars with distinct chemical signatures. Webb's expanded spectroscopic samples provide the statistical power needed to distinguish between competing models, though the data analysis remains ongoing and consensus elusive. The chemical abundance patterns Webb reveals carry implications beyond academic understanding of galactic history. The elements that compose rocky planets, including Earth, came from stellar nucleosynthesis in previous stellar generations. The specific abundance patterns in the gas from which the Sun formed determined which elements were available to incorporate into Earth and the other planets. Stars with very different abundance patterns might host planetary systems with fundamentally different compositions, potentially affecting geological activity, atmospheric retention, and habitability. The metallicity distribution function, the statistical distribution of stellar metallicities throughout the galaxy, represents a key constraint on chemical evolution models. Earlier surveys established the basic shape of this function, but incompleteness in faint and distant stellar populations introduced biases. Webb's deeper observations refine the metallicity distribution by including populations that previous surveys missed, revealing whether the tails of the distribution extend further toward extremely metal-poor or extremely metal-rich objects than earlier data indicated. The radial metallicity gradient, the systematic increase in metal abundances from outer to inner galaxy, has steepened or flattened at different cosmic epochs, according to various theoretical models. Measuring the ages of stars at different metallicities constrains how this gradient evolved over time, distinguishing between models where the gradient formed early and remained stable versus models where ongoing gas flows and star formation continuously modified it. Webb's ability to estimate stellar ages through multiple techniques provides the temporal dimension these analyses require. You absorb the notion that the atoms composing your body passed through previous stellar generations before arriving in the gas cloud that collapsed to form the Sun and planets. The calcium in your bones, the iron in your blood, the oxygen filling your lungs all carry cosmic histories encoded in their nuclear structures. Webb traces these histories across the galactic disk, revealing how elements accumulated over billions of years to produce the chemical environment in which life emerged. The galaxy's chemical evolution is your chemical ancestry, written in abundance patterns that only instruments of exquisite sensitivity can read. The nucleosynthetic signatures Webb helps decode include not just overall metallicity, but the detailed isotopic ratios that distinguish between different production sites. Supernova explosions produce characteristic signatures distinct from the slow neutron capture processes that occur in certain evolved stars. Rare events like neutron star mergers contribute disproportionately to the heaviest elements like gold and platinum. By measuring these isotopic signatures across many stars at different locations and ages, astronomers trace the contributions of various nucleosynthetic processes to the galaxy's chemical budget. The expanded stellar samples Webb provides improve the statistical precision of these measurements, allowing detection of subtle patterns that constrain astrophysical models of how the universe produces its diverse elemental inventory. The azimuthal variations in chemical abundances, variations around the disk at constant radius, provide another dimension of information Webb helps explore. Spiral arms, with their enhanced star formation, might create localized chemical enrichment patterns that propagate through the disk. Interactions with satellite galaxies might introduce chemically distinct material at specific locations. These azimuthal effects are more difficult to measure than radial gradients, but carry complementary information about how the galaxy's chemical composition evolved inhomogeneously rather than uniformly. The warp and wobble of our galaxy now captures your attention as the Milky Way's disk reveals itself to be far from the flat, featureless plane that simple models describe. Webb's observations confirm and extend earlier discoveries that the disk bends, twists and oscillates in ways that betray a dynamic history of gravitational interactions and ongoing perturbations. The galactic disk you conceptually inhabit is not a rigid structure, but a flexible membrane, warped by invisible forces into configurations that challenge theoretical understanding. The discovery of the Milky Way's warp disk dates back to radio observations in the 1950s, when surveys of neutral hydrogen revealed that the outer disk bends above the galactic midplane on one side and below it on the other, like a hat brim with one edge turned up and the opposite edge turned down. This S-shaped warp extends across roughly the outer third of the disk, becoming more pronounced at greater distances from the galactic centre. The cause of the warp remained debated for decades, with proposed explanations including gravitational torques from satellite galaxies, accretion of intergalactic gas at oblique angles, and the influence of the misaligned dark matter halo. Webb's observations extend our knowledge of the warp's extent and structure, revealing that warping persists to greater distances than previous surveys could trace. The faint outer disk populations Webb detects occupy regions where the warp becomes most pronounced, providing traces that map the three-dimensional structure of the disk's deviation from a flat plane. The data suggest the warp may extend further from the galactic centre than earlier estimates indicated, potentially correlated with the extended disk populations that revised our understanding of the Milky Way's overall size. The warp is not static but precesses around the galactic centre like a wobbling spinning top, completing a full circuit in perhaps 1 billion years, according to various theoretical models. This precession means the warp's orientation changes over cosmic timescales, with regions currently bent upward eventually bending downward and vice versa. The precession rate constrains models of what causes the warp, since different physical mechanisms predict different precession periods. Webb's observations, combined with Gaia's proper motion measurements, allow increasingly precise determinations of the warp's kinematics, and hence its underlying cause. Here is the quirky detail that makes the warp particularly interesting. The precession appears too slow to be explained by the gravitational torque from the Magellanic Clouds alone, suggesting additional factors contribute to maintaining and modifying the warp over time. Some models invoke the influence of a tilted dark matter halo, whose non-spherical shape exerts torques on the disk that affect warp dynamics. Others suggest ongoing accretion of intergalactic material at particular orientations keeps refreshing the warp as precession would otherwise damp it away. The debate remains active, and Webb data feed directly into attempts to distinguish between mechanisms. Scientists still argue about whether the warp represents a primordial feature present since the Milky Way's disk formed, or a more recent development triggered by specific gravitational encounters. the age distribution of stars in warped outer regions provide potential constraints, since stars formed in a warped disk should exhibit different spatial and kinematic properties than stars formed in a flat disk that later became warped. Webb's ability to characterize stellar populations in these distant regions enables tests of formation scenarios that earlier instruments could not perform. The vertical oscillations of the disk represent a related but distinct phenomenon, where stellar populations bob up and down relative to the galactic midplane like waves on water. These oscillations, sometimes called corrugations or vertical waves, were detected through Gaia observations and appear to have been triggered by relatively recent gravitational perturbations, potentially including passages of satellite galaxies through or near the disk. The oscillation patterns encode information about the perturbing objects and the disk's response, providing another window into the Milky Way's dynamical history. Webb contributes to oscillation studies by characterizing stellar populations at different vertical heights above and below the midplane. The age and chemical distributions of stars participating in oscillations constrain when the perturbations occurred and how the disk has responded over time. The emerging picture describes a disk far more dynamically active than simple static models suggest, continually responding to gravitational influences from satellites, dark matter structures, and possibly intergalactic gas accretion. The disk's thickness also varies with radius and appears influenced by both internal dynamics and external perturbations. The thin disk, where most star formation occurs, maintains a relatively constant thickness through the inner galaxy, but may flare outward at large radii, becoming thicker as gravitational confinement weakens. The thick disk, an older and more dispersed stellar component, exhibits different behavior that Webb helps characterize through observations of kinematically selected populations at various distances. You envision the Milky Way's disk not as a rigid frisbee, but as a flexible membrane rippling with waves and warps, its outer edges bent and wobbling in response to gravitational tugs from satellite galaxies and dark matter structures. The beautiful spiral arm patterns overlie this warped substrate, rising and falling as you trace them outward from the galactic center. Webb reveals these three-dimensional complexities through patient observation of stellar populations too faint for earlier instruments, building a picture of a dynamic structure far removed from the idealized flat disks that adorn textbook diagrams. The connection between disk warps and the extended halo structure adds another layer of complexity to these analyses. As satellite galaxies orbit through the halo and occasionally pass near or through the disk, they exert gravitational influences that can excite both warping and oscillations. The Sagittarius dwarf galaxy, currently in the process of being disrupted by the Milky Way's tides, has passed through the disk multiple times in its orbital history, and simulations suggest these passages contributed significantly to the disk's current dynamical state. Webb's detailed observations of both the disk populations and the Sagittarius tidal streams allow increasingly sophisticated reconstruction of this interaction history, connecting the warped outer disk to the ongoing cannibalization of a satellite galaxy. The future evolution of the warp depends on continuing interactions with satellites and the dark matter halo, processes that operate on timescales of hundreds of millions of years. Current observations capture a snapshot of an evolving structure, and theoretical models extrapolate both forward and backward to understand how the disk reached its present configuration and how it will change as satellite orbits evolve and accretion processes continue. Black holes hiding in plain sight emerge from Webb's data now, those mysterious gravitational monsters of intermediate mass that theorists predicted should populate the galaxy, but that observational astronomers struggled for decades to confirm. You descend into the darkness between the stellar mass black holes created by individual stellar deaths and the supermassive giants lurking in galactic centers, into the mass range of hundreds to thousands of solar masses, where intermediate mass black holes have long posed one of astrophysics' most tantalizing puzzles. Webb's observations have finally revealed these elusive objects scattered throughout the Milky Way, confirming their existence and providing the first population-level constraints on their abundance and distribution. The black hole census prior to Webb's observations included two well-characterized populations separated by an enormous gap. Stellar mass black holes, created when massive stars exhaust their nuclear fuel and collapse, typically contain 5 to 50 solar masses. These objects manifest through X-ray emission when they accrete material from binary companions, and gravitational wave observations have detected dozens of stellar mass black hole mergers, confirming their existence and constraining their mass distribution. At the opposite extreme, supermassive black holes containing millions to billions of solar masses anchor the centers of most large galaxies, their presence inferred from stellar dynamics, accretion signatures, and the stunning Event Horizon Telescope images of black hole shadows. Between these extremes lay the intermediate mass black holes, hypothetically weighing hundreds to tens of thousands of solar masses, whose existence remained frustratingly uncertain. Theoretical models of star cluster dynamics, early universe physics, and hierarchical black hole growth all predicted that intermediate mass black holes should exist, but observational evidence remained sparse and controversial. A few candidate objects appeared in globular clusters and dwarf galaxy nuclei, but definitive confirmation proved elusive, and the question of whether intermediate mass black holes exist in significant numbers remained open. Webb's contribution to solving this puzzle comes primarily through two channels: the detection of intermediate mass black holes in globular clusters through their gravitational influence on stellar kinematics, and the identification of unusual infrared sources whose properties suggest black holes in the intermediate mass range. The telescope's sensitivity to faint stellar populations in crowded environments allows velocity measurements precise enough to reveal the gravitational signatures of compact masses that could only be black holes. The resulting detections have moved intermediate mass black holes from the category of theoretical speculation into the realm of observed astronomical objects. Here is the quirky detail that makes intermediate mass black holes particularly interesting. Their formation mechanism remains unclear even as their existence becomes established. Stellar mass black holes form from the collapse of massive stars through well-understood physics. Supermassive black holes grow from smaller seeds through accretion over cosmic time. But how do intermediate mass black holes form? Possibilities include the direct collapse of very massive primordial stars, the runaway merger of stars or black holes in dense stellar systems, and the primordial formation of black holes from density fluctuations in the early universe. Different formation channels predict different spatial distributions and mass functions, and Webb's observations of intermediate mass black hole populations begin constraining these theoretical alternatives. Scientists still argue about whether the objects Webb has identified truly qualify as intermediate mass black holes, or might have alternative explanations, including unusual stellar configurations or instrumental artifacts. The historical record of supposed intermediate mass black hole detections includes numerous candidates that subsequent observations downgraded or disproved entirely, making the community appropriately cautious about claiming definitive detections. Nevertheless, the accumulating evidence from multiple independent Webb observations strengthens the case that these objects exist and populate the galaxy in meaningful numbers. The distribution of intermediate mass black holes throughout the Milky Way carries implications for stellar dynamics, gravitational wave astronomy, and the history of structure formation. If these objects populate globular clusters as Webb suggests, their gravitational influence affects how those clusters evolve over time, potentially explaining observed discrepancies between cluster properties and theoretical predictions. The population also represents a potential source of gravitational waves when intermediate mass black holes merge with stellar companions or with each other, events that future gravitational wave detectors may observe directly. The connection between intermediate mass black holes and the formation of supermassive black holes at galactic centers represents one of the most significant implications of Webb's discoveries. If intermediate mass black holes form in large numbers throughout galaxies and gradually migrate towards centers through dynamical friction, they could provide the seeds from which supermassive black holes grow. This hierarchical assembly scenario competes with alternative models where supermassive black hole seeds form directly through massive gas cloud collapse, and observations of intermediate mass black hole populations help distinguish between these formation pathways. You contemplate the darkness scattered throughout the galaxy, gravitational monsters of intermediate size lurking among the stars, invisible except through their influence on surrounding material. Webb cannot image these black holes directly, no telescope can, but it reveals their presence through the motions of nearby stars and the properties of accreting material that betrays invisible companions. The Milky Way's black hole population extends beyond the stellar corpses and central giant into the intermediate regime that long eluded detection, filling a gap in our understanding that theorists identified decades ago and observers have finally begun to close. The gravitational wave implications of intermediate mass black hole populations deserve particular attention as you drift towards sleep. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves at frequencies too low for ground-based detectors like LIGO, frequencies where intermediate mass black hole mergers would produce signals. Webb's constraints on intermediate mass black hole populations inform predictions for LISA detection rates, allowing mission planners to optimize observing strategies for the expected source populations. The connection between electromagnetic observations from Webb and future gravitational wave observations from LISA illustrates the increasingly multi-messenger nature of modern astrophysics, where different observational windows complement each other in revealing cosmic phenomena. The historical context of intermediate mass black hole searches extends back decades, with generations of astronomers proposing candidates that subsequent observations could not confirm. The frustration of repeatedly finding that supposed detections had alternative explanations made the community skeptical of any individual claim, requiring extraordinarily robust evidence before accepting intermediate mass black hole identifications. Webb's ability to provide that robust evidence through multiple independent observations represents a genuine breakthrough in a field that had experienced too many false starts and premature announcements. Recalculating our cosmic address becomes necessary now, as the Milky Way's revised scale ripples outward through ever larger structures, changing our understanding of where we fit within the local group, the local supercluster, and the observable universe beyond. You zoom out from galactic scales to contemplate how a larger, more massive Milky Way repositions us within the cosmic web, that vast network of filaments and voids that represents the larger scale structures in existence. The local group of galaxies, that gravitationally bound collection of roughly 80 known members, dominated by the Milky Way and Andromeda, acquires new characteristics when its largest members' mass and size are revised upward. Gravitational influence extends further from a more massive galaxy, potentially bringing additional dwarf galaxies into the local group's domain and affecting the orbital dynamics of known members. The calculations that predict satellite orbits, merger timelines, and the eventual fate of local group members all depend on mass distributions that Webb's observations help constrain. The historical mapping of the local group proceeded through patient accumulation of distance measurements, velocity determinations, and gravitational binding assessments that sorted nearby galaxies into members versus passing strangers. The membership list grew steadily as surveys detected fainter and fainter dwarf galaxies orbiting either the Milky Way or Andromeda, with the current count exceeding 60 confirmed satellites around our galaxy alone. Webb's discoveries of additional ultra-faint dwarfs and improved characterization of known members continue expanding and refining the local group census. Beyond the local group, the local volume encompasses all galaxies within roughly 30 million light-years, including isolated dwarfs, small groups, and the nearest large structures like the Sculptor group and the Maffei group hidden behind the Milky Way's disk. The Milky Way's gravitational influence extends into this volume, affecting the peculiar velocities of nearby galaxies and contributing to the overall dynamics that determine how structures in the local volume will evolve over cosmic time. Here is the quirky detail that makes our cosmic address particularly interesting. Despite having accurate distance measurements for thousands of galaxies, astronomers cannot precisely specify our location within the local volume because there is no absolute reference frame against which to measure position. We can determine distances and velocities relative to other objects, but cosmic expansion has no center, and our position can only be described relationally. A more massive Milky Way changes the relationships that define our cosmic address, without changing the fundamental difficulty of locating ourselves within a centerless universe. Scientists still argue about the boundary conditions that define where the local group ends and the general field begins, a question that a more massive Milky Way complicates by extending gravitational influence further than previous models suggested. The turnaround radius beyond which objects recede due to cosmic expansion, rather than falling toward the local group barycenter, shifts outward if the local group's total mass increases. This shift affects predictions for which galaxies will eventually join the local group as bound members versus which will recede forever into the expanding universe. The local supercluster, also called the Laniakea supercluster, represents the next scale of cosmic structure, containing the local group along with thousands of other galaxies spread across roughly 500 million light-years. The Milky Way occupies an outlying position within Laniakea, located in a sparse filament rather than in the densest concentrations near the Virgo cluster at the supercluster's heart. Our cosmic address, increasingly precise yet increasingly humbling, positions us in the galactic suburbs of a structure whose full extent was only mapped in the 2000s. The peculiar velocity of the Milky Way, its motion relative to the cosmic microwave background radiation that provides the closest thing to an absolute rest frame the universe possesses, reflects the gravitational influences of all surrounding structures. The local group falls toward the Virgo cluster, while also being pulled by the Great Attractor and other mass concentrations at greater distances. A more massive Milky Way changes the local group's total momentum and affects calculations of how these various gravitational influences combine to produce our observed peculiar velocity. The large-scale structure of the universe, the cosmic web of filaments and voids that emerge from primordial density fluctuations, provides the context within which all smaller structures exist. The Milky Way resides in a filament of this web, connected to the Virgo cluster through streams of galaxies and intergalactic gas that trace the web structure. Webb cannot image this large-scale structure directly, but its observations of the Milky Way and local group members contribute to the gravitational accounting that reveals how mass is distributed throughout our cosmic neighborhood. You recline into the contemplation of nested addresses, each scale larger than the last, a planet orbiting a star in the Orion spur of a galaxy, now known to be larger than your education suggested, in a local group dominated by that galaxy and its Andromeda rival. in an outlying position within a supercluster whose center lies 50 million light-years away, embedded in a cosmic web whose filaments stretch across the observable universe. The revision of the Milky Way's scale propagates through each level of this hierarchy, changing the numbers that describe where we are without changing the fundamental fact of our embedded existence within structures so vast that comprehension fails long before observation does. The peculiar velocity field of the local volume, the pattern of galaxy motions relative to the smooth Hubble expansion, encodes information about the distribution of matter, both visible and dark, throughout our cosmic neighbourhood. A more massive Milky Way contributes more strongly to this velocity field, affecting how nearby galaxies move relative to the cosmic background. Cosmologists use velocity field measurements to infer mass distributions independently of direct observations, and consistency between these dynamical mass estimates and masses derived from other techniques like rotation curves and lensing provides important cross-checks on our understanding of cosmic structure. Webb's constraints on the Milky Way's mass feed directly into these cosmological calculations. The cosmic flow patterns reveal structures beyond the local supercluster that influence our motion through space. The Great Attractor, a mass concentration roughly 200 million light-years away in the direction of Centaurus, was discovered through its effect on galaxy peculiar velocities and remains incompletely characterized due to obscuration by the Milky Way's disk. Webb's infrared observations can potentially penetrate this zone of avoidance, revealing structures hidden from optical surveys and clarifying the mass distribution responsible for the Great Attractor's pull. Our cosmic address exists within gravitational fields extending across hundreds of millions of light-years, and understanding our position requires mapping masses at correspondingly vast scales. What Webb still cannot see deserves acknowledgement now, as even humanity's most powerful space telescope confronts limitations and mysteries that its magnificent instruments cannot resolve. You pause here to contemplate the boundaries of current knowledge, the questions that remain unanswered despite Webb's transformative observations, and the humility that genuine scientific understanding requires. The Milky Way's revised scale represents an enormous advance in our understanding, but it simultaneously reveals how much remains unknown and how provisional even our best current knowledge must be considered. The dark matter that dominates the galaxy's mass budget remains fundamentally mysterious, despite Webb's improved constraints on its distribution. Webb cannot directly image dark matter because dark matter does not interact with light, by definition invisible to any electromagnetic telescope, regardless of wavelength sensitivity. The dark matter, Halo's existence, is inferred entirely from gravitational effects on visible tracers, and while Webb improves those tracers' quality and quantity, it cannot reveal what dark matter actually is. The particle nature of dark matter, if indeed it is a particle, remains one of physics' deepest unsolved problems, untouched by Webb's astronomical observations. The earliest epoch of the Milky Way's formation predates the oldest observable stars and leaves no directly detectable signatures in the present-day galaxy. Population 3 stars, the theorized first generation composed purely of primordial hydrogen and helium, have never been observed despite dedicated searches. Their nucleosynthetic products survive in subsequent stellar generations, but the objects themselves exploded billions of years ago, long before any currently observable star formed. Webb's ability to detect ancient population 2 stars approaches the closest possible link to this primordial era, but a gap remains between the earliest observable objects and the very first moments of galactic assembly. Here is the quirky detail that captures the limits of observation. Webb's infrared sensitivity, while unprecedented, still operates at finite wavelengths and sensitivities that exclude certain phenomena from detection. Objects colder than a few tens of Kelvin emit primarily at wavelengths longer than Webb observes efficiently. Objects so deeply embedded in dust that even infrared radiation cannot escape remain hidden. Objects too faint or too distant fall below Webb's detection thresholds regardless of wavelength. Every telescope, no matter how powerful, sees only those objects that emit detectable radiation within its operating parameters, and the universe surely contains phenomena that no current instrument can perceive. Scientists still argue about how much of the Milky Way structure can be understood from observations within the galaxy versus how much requires the external perspective that only observations of similar galaxies can provide. Our embedded position within the disk prevents the kind of bird's-eye view that makes external galaxies appear so photogenic, and while Webb's observations improve our internal mapping, the fundamental limitation of perspective remains. Comparing the Milky Way to external spiral galaxies helps constrain what we cannot directly measure about our own system, but such comparisons assume our galaxy resembles others in ways that may not always hold. The time domain represents another limitation that even Webb's long-duration observations cannot overcome. Galactic processes unfold on timescales of millions to billions of years, far exceeding any conceivable observing program. The spiral arms that currently adorn the Milky Way will dissolve and reform, the stellar populations will age and be replaced, the dark matter halo will merge with Andromeda's, all on timescales no observer can witness. We see the galaxy at a single moment in its history, able to infer past and future from the frozen snapshot Webb provides, but unable to watch the actual processes unfold. The theoretical models that interpret Webb's observations carry their own uncertainties and potential errors that propagate into conclusions about galactic properties. The conversion from observed brightness to stellar mass requires assumptions about stellar evolution that may be incorrect in certain regimes. The inference of dark matter distribution from stellar kinematics requires assumptions about halo shape that remain poorly constrained. The chemical evolution models that interpret abundance patterns simplify complex three-dimensional mixing processes into tractable approximations. Every conclusion Webb enables rests on theoretical frameworks that future observations may revise. The cosmic mysteries that Webb cannot address extend far beyond the Milky Way into questions about the universe's fundamental nature. The origin of cosmic structure, the nature of dark energy driving accelerated expansion, the potential existence of other universes beyond our cosmological horizon, the ultimate fate of everything, all lie beyond even Webb's considerable reach. The telescope reveals an expanded Milky Way within an expanding universe, but the deepest questions about why anything exists at all remain philosophical rather than observational. You rest with incompleteness, comfortable perhaps in the understanding that knowledge always has edges, that the most profound questions resist easy answers, and that scientific progress consists not of final solutions, but of better and better approximations to truths we may never fully grasp. Webb has revealed a larger Milky Way than our ancestors imagined, but it simultaneously reveals how much larger still our ignorance remains. The mystery does not diminish with discovery, but deepens, each answered question spawning further questions in an infinite regression that defines the scientific enterprise. The future observations that will extend beyond Webb's capabilities already occupy astronomical planning committees. The next generation of extremely large ground-based telescopes, with mirrors exceeding 30 meters in diameter, will provide complementary data that neither Webb nor current ground facilities can obtain. Space missions currently in development will observe wavelengths and phenomena Webb does not address. The gravitational wave observatories planned for the coming decades will reveal information about black holes and dense matter that electromagnetic telescopes cannot access. Each new facility will answer questions Webb raised while posing questions of its own, continuing the endless cycle of discovery and inquiry. The limitations of human cognition may represent more fundamental constraints than any telescope's technical specifications. The Milky Way contains hundreds of billions of stars across 200,000 light-years, numbers and distances that exceed intuitive comprehension, despite our ability to write them down. We manipulate these concepts mathematically, without truly grasping what they mean, using analogies and approximations that capture aspects of reality without reproducing its full scale. Webb's observations push against the limits not just of instrumentation, but of imagination, revealing a universe whose grandeur exceeds what minds evolved on African savannas can comfortably process. Your place in a vast new galaxy awaits final contemplation now, as the journey through Webb's discoveries about the Milky Way's true scale draws toward its close. You have travelled from the chaotic centre where stars swarm around a supermassive black hole, through spiral arms more complex than any textbook diagram, past satellite galaxies being devoured and stellar streams tracing the ghosts of consumed companions, to the faint outer reaches where ancient stars witness cosmic time from near-empty vistas. The galaxy you inhabit has revealed itself to be grander, more massive, more ancient, and more mysterious than the familiar estimates you might have learned, and your position within this expanded structure deserves a moment of quiet recognition. The numbers have doubled or nearly so, a disk extending perhaps 200,000 light-years rather than 100,000, a stellar population approaching 500 billion rather than a few hundred billion, a dark matter halo exceeding 1 trillion solar masses rather than the lower estimates that once seemed plausible. These revisions transform the Milky Way from a modest spiral galaxy into one of the local group's dominant members, comparable in scale to Andromeda rather than clearly subordinate. The home galaxy you casually reference in everyday speech, if you reference such things casually, is a more impressive address than previous generations appreciated. The personal implications of existing within this expanded structure are simultaneously profound and utterly inconsequential. Your daily life proceeds identically, whether the nearest spiral arm stretches 50,000 or 100,000 light-years from your location. The coffee you drink, the air you breathe, the ground beneath your feet remain unchanged regardless of how many stars occupy the galactic halo. Yet knowing about the revised scale changes something subtle about the context within which that daily life unfolds, connecting mundane existence to cosmic proportions that dwarf imagination itself. Here is the quirky detail that brings this all back to human scale. The light currently reaching Webb from the Milky Way's outermost detected stars left those objects before anatomically modern humans evolved. The photons that carry information about distant stellar populations began their journeys when Earth hosted different species, different climates, different continental configurations than today. The galaxy's vast distances mean that even light, the fastest thing in the universe, requires timescales longer than human history to traverse from edge to center. You exist at a moment in that photonic journey, receiving information from cosmic sources that sent their messages before anyone was present to receive them. Scientists still argue about almost everything Webb has revealed, and this arguing represents science working as intended, rather than any failure of method or evidence. The uncertainties that accompany Webb's discovery should not dismay you, but rather reassure you that scientific claims remain tentative, open to revision, responsive to better data and arguments. The Milky Way's revised scale represents current best understanding rather than eternal truth, and future observations will surely modify today's conclusions in ways we cannot predict. This provisionality defines honest inquiry, distinguishing scientific knowledge from dogmatic assertion. The wonder that Webb inspires derives not just from the technical achievement of placing a tennis court-sized mirror at the second Lagrange point, but from the cascade of understanding that achievement enables. Each infrared photon Webb collects carries information across cosmic distances, and the accumulated photons reveal structures and populations hidden from every previous instrument. The galaxy emerging from this photonic census exceeds expectations formed by optical observations, rewarding the investment of time, money, and ingenuity that Webb required with discoveries that genuinely expand human knowledge. You belong to a species that built this telescope, that conceived and executed a plan to see the invisible, that refused to accept the limitations of evolved senses and extended perception into wavelengths evolution never selected for. This capacity for transcending biological constraints defines humanity as much as any other trait, and Webb represents its current pinnacle in a tradition stretching back through Hubble and Palomar and Mount Wilson and Galileo's first telescope to the first curious hominid who looked up and wondered what the lights in the sky might be. The Milky Way's revised scale answers questions those ancient ancestors could not have formulated, connecting their primal curiosity to your present understanding through an unbroken chain of inquiry. The journey tonight has carried you across scales your intuition cannot truly grasp, from black holes smaller than our solar system to disk structures spanning 200,000 light-years. Webb's infrared eyes have guided this journey, revealing what visible light cannot show and populating the galaxy with stars nobody knew existed. The dark matter halo extends invisibly around everything. The spiral arms wind in fractal complexity. The satellite galaxies fall inward toward eventual consumption, and the ancient relics at the edge witness time passing on scales that make human history seem instantaneous. This is your home, expanded and deepened by Webb's observations, and knowing its true scale changes nothing about daily existence, while transforming everything about the context within which that existence unfolds. The stars continue their ancient circuits as your breathing slows, each one a sun with its own story, most of them invisible to human eyes yet present nonetheless in numbers too vast to count. The Milky Way stretches overhead whether you can see it through city lights or not, its disk extending further than you learned, its spiral arms winding with complexity no textbook captured, its dark matter halo cradling everything in invisible gravitational embrace. Let the numbers fade now, the billions and trillions dissolving into the softer mathematics of rest. The galaxy will continue its slow rotation, whether you witness it or not. The stars will burn and die, and be replaced by new generations formed in spiral arm nurseries. The satellite galaxies will drift inward toward their eventual consumption, all on timescales so long that tonight's sleep represents less than an eye blink in cosmic terms. Your body relaxes into the knowledge that you exist within something immense, something ancient, something revealed more fully now than ever before by instruments of extraordinary sensitivity floating in the cold darkness beyond the moon's orbit. The James Webb Space Telescope keeps its golden eye turned toward the infrared sky, while you drift toward dreams, collecting photons that will become tomorrow's discoveries, building understanding that future generations will inherit and extend. The Milky Way holds you gently, its gravity barely noticeable at human scales yet sufficient to bind hundreds of billions of stars into a single rotating structure. You're part of this structure, your atoms forged in stellar cores that exploded before the sun existed. Your consciousness emerging from chemistry that cosmic processes made possible. Rest now within this expanded home, this galaxy grander than your education suggested, this island of light in the vast darkness between galaxies. Sleep well beneath stars too numerous to count, in a galaxy too large to comprehend, cradled by mysteries that deepen with every discovery. Sweet dreams,